Buongiorno a tutti.
Buongiorno Cristian. Okay.
Allora, the chairman of this morning is Riccardo Cerulli from Tor Vergata University and INFN. Roma 2, please.
Good morning to everybody. We are the second day of this school. So I think that we can start now the first lecture. The lecture will be given by Cristiano Galbiati, that is a leading role in the astroparticle physics field. He's a full professor at Princeton University and also a full professor at the Gran Sasso Science Institute. He participated to a lot of underground experiment in neutrino physics and dark matter. He has been the spokesperson, co-spokesperson of the Borexin experiment, and also the principal investigator and the spokesperson of warp and dark side at the moment. That is one of the most important dark matter experiment at Gran Sasso and in the world. So I think that Cristiano, you can start, and he will talk about the Nobel liquid detectors. That is a technique very well considered and used for the dark matter search. So I propose you can, if you can make a break after a first part of the talk. So if someone has some quick questions, you can answer, and then you can start again to conclude the second part of the lecture, if you agree, Cristiano.
So you would like to have a break in the middle of the lecture?
Yes, it would be better. In order, so if someone has some questions, you can answer, and also you can take a breath and I don't know, drink a glass of water.
A coffee. Okay.
Okay.
Very good.
Perfect. Let's start.
I will start and I will share the screen. Okay. Can you see the slides if I enter in this presentation mode?
Yes.
And you can see them moving.
Yes.
Right?
Yes. It's working.
Okay, so noble liquid detectors, why they are important and why they are having such a prominent role in these decades in the research in astroparticle physics. There are a few reasons. They are cold. They can be purified. By cold and can be purified, I mean the targets, the noble liquid targets. There is also two very important features of these noble liquid targets. The attachment probability for the electrons is essentially null. It's very, very difficult for one of these noble atoms to capture an electron. And the reason is very simple, is because they have very complete shells in the atomic model, which is something that you should be very familiar with. What this means is that you can drift the charge for very, very long distances. So you can get out the signal, the primary signal from ionization for very, very long distances. The second thing that happens is something which is a little bit more difficult to understand from the first principle, but it's a fact of nature which is very important. This material, they all scintillate. They all emit scintillation light. So when you ionize a target, not only you get the ionization electrons, but you also get a portion of the energy converted into scintillation light, which is typically in the near or far ultraviolet. And even very important, the self-absorption of the scintillation light is essentially negligible. And this scintillation light can travel for very, very long distances, maybe not in a straight path, because there is a significant Rayleigh scattering, but you can travel, you can have a scintillation light that is traveling for very, very long distances. And so based on these two topics, you can have detectors on which you can get two complementary detection channels, charge and light. And this is very important because it gives you access to two fundamental tools of discrimination. One is discrimination based on the EDX, and the second, sorry for the incomplete sentence here, but something happened at the last minute. And the second is the dependence of the time decay of the scintillation upon the density of the ionizing tracks. The first experiment that took advantage of these novel liquid targets is the Icarus experiment. Icarus, it's a time projection chamber whose development starts in the 70s, thanks to Carlo Rubbia, who had a lot of influence in the development of this entire field, both on the neutrino side and on the dark matter side. And Icarus was originally invented in the 70s when the highest problem in astroparticle physics was actually not neutrinos. Neutrinos was an afterthought, but was proton decay. Okay. In the 70s, people were after the so-called grand unification scheme. The holy grail of astroparticle physics was the observation of proton decay, which was a common staple of all the grand unification theories, and was the sort of holy grail of the unification of the forces beyond the step of unification of the electric and the weak force. And so for this reason, Icarus was developed as a tool to be able to observe with a very strong precision some peculiar events having to do with the proton decay. And of course, it was immediately realized its immense power for neutrino physics, being able to resolve with very strong capability tracks for neutrino physics, not only high energy neutrinos, such as those fired by an accelerator, but also potentially low energy neutrinos. One of the main objectives of the initial proposal of Icarus, very few people remember, but was the observation of neutral and charged currents, like very much like the SNO experiment did, but utilizing some charged current reactions on argon. And one of the early proponents, together with Carlo Rubbia, of this methodology was the late John Bacall, who had a very singular and very strong influence on the development of neutrino physics across these decades. The main tool of Icarus, the detection of charge. Charge is observed on two planes, an induction plane where you see the signal which is induced by the passage of the charge, and a collection plane where you see the signal which is caused by the collection, the direct collection of the charge. The scintillation light for this kind of detector is simply used to set the T0 of the event. Some typical parameters of these detectors: a drift velocity of approximately 500 volts per centimeter. The rule of thumb is that with a drift velocity between a few hundred and 1 kilovolt per centimeter, you have essentially a speed of drift which is of the order of the centimeter per microsecond. Icarus operated finally in Gran Sasso during the early years 2000 as a detector for neutrinos that were coming from the so-called CNGS, CERN Gran Sasso Neutrino Beam. And when it completed its mission as part of this exploration of the beam of neutrinos of CERN to Gran Sasso, was repurposed in Fermilab for the study of short baseline neutrinos. The main result of Icarus in the so-called CERN2 Gran Sasso beam was the one of essentially clearing up the signal that had been touted by the Opera collaboration of a superluminal neutrino. Icarus was perhaps the first experiment reporting the fact that the time of flight for the neutrinos was indeed in line with the expectations. You see here some beautiful signals collected with the Icarus experiment in Gran Sasso that give you an idea of its power of resolution, the ability of separating muons and kaons in the detector, and to have a very, very efficient identification of the particles based on the precise 3D reconstruction on the EDX. Here you see some Monte Carlo events that pertain to the potential operation of Icarus at Fermilab. And you see here the beautiful ability of this detector of identifying even the very precisely the measurement of the muon momentum via simply the reconstruction of the multiple scattering and via the reconstruction of the DEDX along the track of the muon. The goal of Icarus in this new form and in this new shape at Fermilab is the one of clearing up some anomalies on short-range oscillation of neutrinos. This field of the anomalies, for those of you that are new into this field, started a long time ago. A long time ago, and I say in the last portion of the past century. From 1995 through 1999, one of the big players in the field was the so-called LSND, a liquid scintillator neutrino detector operating at Los Alamos, with the neutrinos generated on an 800 MeV proton beam at the Lancy accelerator in a water target with a copper beam stop. The reaction of production of the neutrinos, mostly mu and anti-mu, was the one I highlighted here. And what they saw, this experiment, was an excess of anti-electron neutrino, which they attributed to oscillations of neutrino at a very short baseline. Now, this experiment was fully tested by the mini-boon experiment, which found no trace of this oscillation, essentially denied the signal that was observed by the LSND experiment, but came up with its own anomaly, an excess of neutrinos that were populating a very low energy region of the spectrum. And so for this reason, the anomaly is still in play. And there are many experiments in Fermilab that are trying to address this anomaly. Not only Icarus, but also another experiment, which is part of the so-called SBND, the short baseline neutrino program at Fermilab, which is the so-called microboon detector, which is another detector which utilizes liquid argon in a time projection chamber format. Very close in the way the TPCs arranged to the Icarus experiment. It was the first very big liquid argon TPC built at and by Fermilab, but at the very same time, very different in terms of the cryogenics. One recent element which is compounding the interest into this field is the observation, or at least touted observation, of sterile neutrino reported by the so-called Neutrino 4 experiment. The Neutrino 4 experiment, which is examining in Russia a so-called, neutrinos that are coming from the reactor, and that has seen a possible oscillation of these neutrinos. And this is also an experiment which is worth to be probing in detail with the short baseline neutrino program. And both the Icarus experiment at Fermilab and the microboon experiment at Fermilab are very well poised to test these anomalies. The anomaly which is coming from the low energy signal of the mini-boon experiment and this possible signal coming from the neutrino 4 experiment. So it's a field which is ripe of interest, which is full also of possible anomalies due to the low energy characteristics of these events, the low energy nature of this event. And what we hope is that with the advent of this short baseline neutrino oscillation experiment, Icarus and microboon, which have a much higher resolution in terms of determining the topology of the events than any of the previous experiments, we may be able indeed to come to a full resolution of this anomaly by being able to interpret in detail the nature of these neutrinos. You see here some of the rationale, again, for these kind of searches. This is summarized by another Italian physicist, Angela Fava. Angela grew up at Gran Sasso on the Icarus experiment and now is a very big player in terms of being a very strong actor in the development of the short baseline program at Fermilab. And you see here LSND quoted for the oscillations of muon antineutrinos into electron antineutrinos with a significance of 3.8 sigma. Mini-boon, some anomalies that are quoted at the level of 4.5 sigma and 2.8 sigma. This is a little bit controversial, I have to say, because the Mini-boon collaborators had a very first paper that was extremely clear in rejecting the anomaly proposed by LSND. And then as the year came by and some of the original people in the collaboration left, through some much more detailed analysis, anomalies started popping up, but at low energies, in energy regions that were not exactly the same where the LSND anomaly was found. Galax and SAGE, an anomaly for MUE disappearance at the level of 2.8 sigma. Also here, I have to say this is a little bit controversial because Galax and SAGE, for those of you that don't know much about it, those were two storied experiments in the era of solar neutrinos, really heroic experiment at the time when people were looking for radioactive atoms, individual radioactive atoms generated in tens of tons of materials triggered by solar neutrinos. Okay, the experiment were boiling down to collecting these radioactive atoms that had accumulated in liquid targets over the span of many, many months. And the Galax and SAGE collaborators, again, never claimed any discrepancy with a specific oscillation model. You know, they just reported their data, and this discrepancy were found by theorists many years later, but I'm not sure that the original experimenters would agree with this interpretation. Anyhow, as you see, between these and the new anomalies that are coming out from the reactors, specifically the neutrino 4 experiment, there is a lot of room for the possibility that an interesting signal may still lie in place and may still be able to be discovered through one of these experiments. For this reason, at Fermilab, the short baseline neutrino program is taking place. And it's a very complex program, which is based on 3 different detectors. There is the so-called SBND, which is a short baseline detector aiming at probing and characterizing the beam of neutrinos that are coming out of the booster target. And then there are 2 detectors, microboon and Icarus. 86-ton microboon, you see the detector being lowered in the pit, and 470 tons Icarus at 2 different distances, 470 meters and 600 meters. So the goal of SBN is to clear up once and hopefully for all this problem of low energy short baseline neutrino oscillation. And I say low energy because the anomalies that are coming from previous experiments typically tend to cluster in the region which has the poorest understanding, and it's the region of lowest energy of these neutrinos. At the very same time, this program will have the advantage of being able to boost the technical preparation of Fermilab for the so-called DUNE experiment, which is the Deep Underground Neutrino Experiment, which is the flagship program for Fermilab. It consists in shooting a beam of neutrinos, high-energy neutrinos, over 800 miles from Illinois, from Chicago, from the Fermilab near Chicago, where the accelerator complex is sited, to South Dakota, to the so-called Sanford Underground Research Facility, SURF, where big cavities are being excavated at this moment in time to host a detector that with its 4 units will have one day a combined mass of 40,000 tons of liquid argons. The neutrino beam will be generated by 8 GeV protons from the booster complex at Fermilab, will be shot off to South Dakota using a new neutrino line, separated from the previous neutrino line that fed the site in Minnesota where Minos and Nova have been sited. The technology is once again the one of the liquid argon TPC, so the same technology that has been explored initially by Icarus and that has been used with so much success in the short baseline program, so much technological success for the moment in time, and we will soon get at seeing the physics out of it. The idea is to have this very massive and homogeneous target of 40,000 tons with excellent tracking and calorimetric capabilities, but also a truly excellent coverage for the scintillation light. The scintillation light is phenomenal and fundamental to extract information from low energy neutrinos, to explore also supernova neutrinos, to explore neutrinos from the sun, which are in the range of a few tens of MeV, or in the case of the sun, they come down to 20, 15, 10, down to 8 MeV. 8 MeV is the lowest possible threshold for the argon program, because below this level, there is a lot of background induced from neutrons in the detector. And once again, what is the characteristic of this detector? As we saw before, it's the incredible ability to reconstruct in 3 dimensions in time the tracks of the particles, an incredible ability in separating the typology of particles depending on their DDX, depending on the track, depending on the topology of the detector, and so forth. For the SBND, we expect to have the world highest statistics for the cross-section measurements of argon, on argon. In 3 years, we expect to collect something like 7 million neutrinos, which is a huge sample. Okay? For somebody like me who started when we were counting, we were seeing the best experiment of solar neutrinos to report just a few neutrino events. This is an incredible statistical sample. So 7 million events of muon neutrinos and 50,000 electron neutrinos. Icarus is going to expect of the order of 10 to the 5 events per year. The microboom, which has already been operating for a few years, we expect any moment, any summer, probably this summer, to have a first results on the physics of the experiment. And as I said before, the goal is really the one of clearing up several anomalies that are appearing at low energy. Some more details on the detector themselves. SBND, 260 tons of liquid argon, 112 active. It's a combined of 2 TPC with 2 PMT drifts. Detection of the light is trusted to 120 8-inch PMTs, but also 192 X-Arapuca. X-Arapucas are detectors that are based on a new type of silicon photosensors that will be highlighted very strongly during this week, silicon photomultipliers, covered by a 4-pi cosmic ray tagger. And we said a little bit before, Microboom and Icarus, respectively 86 and 476 tons of liquid argon time projection chamber, a drift that ranges from the 2.5 meters of Microboom to the 1.5 meters of Icarus. The one element that you should keep in mind is that in this case, being detectors that have been built and finalized a few years ago, the light detection is all trusted to photomultipliers without the use of any silicon photomultipliers, which is a recent, fairly recent innovation and introduction. Once again, the final goal of the Fermi laboratory is the one of developing this huge detector, 40 kilotons of liquid argon, time projection chamber, coupled with a highly capable near detector complex. The accelerator feeding the neutrino beam has some unique characteristics, 1.2 megawatts, upgradable to 2.4 megawatts, which is an incredible number for a beam, an incredible power for a beam of this kind. Produced at Fermilab and sent to South Dakota. The goal of Dune is even more ambitious than the one of the short baseline experiments. The goal is the one of probing the entire matrix of oscillation of neutrinos and discovering the few parameters that are still not known today. So the physics goal in particular is the one of the measurement of the leptonic CP valorization, fully determining the neutrino mass hierarchy, and a precise measurement of the matrix of oscillation parameters, the so-called PMNS parameters. So a very, very ambitious program with a lot of physics coming out from these parameters. Besides the very deep and large-scale detectors that are going to be sited in South Dakota, there is also a very interesting and especially interesting program for the near detector complex, which is separated from the so-called SPND suite that is being pushed for the short baseline oscillation program. The near detector complex is based on 3 different detectors. The so-called near detector in liquid argon, the so-called near detector in gaseous argon, and SAND, a detector which is a non-axis system for neutrino detection, which will have a very, very strong contribution from the Italian group. The primary goal for the near detector complex is the one of fully constraining the uncertainties in the near to far extrapolation of the measurement of flux, cross-section, and neutrino energy in order to enhance as much as possible the sensitivity of Dune for the leptonic CP violation. And in particular, you see here in the lower right corner what is the Dune sensitivity depending on the true value of delta CP over pi. You see, it's very important for reaching a sensitivity, a nominal sensitivity that goes as much as possible above the 5 sigma. Is very important to have a very good characterization of the beam with the near detector. Because if you go with the far detector only, you never get at the full determination of the delta CP, which reaches the 5 sigma level. If you go instead with the presence of a full detector that is able to being completely characterized by a near detector system, which is composed of 3 detectors, you can have an excellent coverage in terms of reaching a 5 sigma discovery power across almost the entire spectrum of the values of delta CP. The first near detector of the near detector complex is the so-called ND-LAR. detector. Same target nucleus, of course, as the fire detector, 50 tons of fiducial mass, and a modular design, which is designed especially to mitigate the high events rate, which is characteristic of the near location. And this is a detector which is characterized in particular by a so-called pixelated readout, so very, very fine readout of the charge. The gaseous argon detector has some key design feature, which is a high pressure gas argon TPC at the core, which will be an almost exact replica of the Alice TPC. And they have acquired indeed the multi-wire chambers that will be repurposed for this very special purpose. It's going to be operated with a 90-10 gas mixture of argon and methane, and is going to be surrounded by an electromagnetic calorimeter and a superconducting magnet. And the sun detector, which is a proposal from the Italian groups, is going to be designed to measure the on-axis beam. It's going to be a combination of the Chloe magnet and an electromagnetic calorimeter with some straw tube tracker detectors. And the design is at this moment in time being finalized for a future review. And we'll have some very, very significant capabilities together with ND-LAR and ND-GAR to constrain the parameters for the understanding of the neutrino beam. So with this one, I will move forward to tell you that based on all of this preparation, we expect this portion of the program on the neutrino physics done with noble liquid to provide really incredible information with the goal of clearing up with the Icarus and Microbloom program, with the SB&D program, clearing up once and for all a series of long-standing anomalies that have been there in the field for nearly 30 years. And I produced no confirmations, but a series of hints that are not of the highest quality, but they need to be pursued and understood and either confirmed or rejected. And at the very same time, with the very long baseline program, the goal of Fermilab is the one of being able to address and fix once and for all the problems of measuring completely the oscillation parameter of the neutrinos and understanding in the greatest gory detail all the parameters of the PMNS matrix that governs the neutrino oscillations. In addition, these detectors will have outstanding capabilities to extend the search for proton decay that remains one of the great objectives and one of the great goals of astroparticle physics. And you see here, for example, some of the abilities of the detector to look in one golden channel, which is the channel created by the decay of the proton in an antineutrino and a kaon plus. You see the stunning level of resolution that comes at a Monte Carlo level from a detector of the type of Dune. Okay, with this slide, I've concluded the portion of my talk that is devoted to novel detectors in the field of neutrino physics. And Mr. Chairman, I would like to ask if this is an appropriate moment for taking a break before I venture into dark matter.
Yes, okay. If there are any questions by the audience, it's the moment to ask regarding this part of your presentation.
I hope I can answer the questions. So.
Yes, for sure.
Giovanni Volta.
Giovanni Volta.
Hi, I have a question. I have a few questions. So you say that the scintillation light for argon you just use for timing. So Dune doesn't have any Z reconstruction. Do you hear me?
Yes, I hear you. So in the detectors of the style of the original Icarus, okay, the scintillation light is essentially used only to provide the T0, which means that you get the X and Y position of the events based on the projection of the events on the wires. And if you have the T0, which is given by the scintillation light, then you can determine the depth, okay? So that's how it works. You get the XY position from the wires. You get the relative position in the Z by the timing of the events in the track as they come to the field of view, which is given by the two wire planes. But the absolute value of the depth, in order to know the absolute value of the depth in Z, you must have the time 0 of the start of the event. And that is what is provided by the scintillation light.
Why you don't use it also for the energy? That's one, or?
Not using for the energies because in the early detectors for high energy neutrinos, the team of scintillation light detection at cryogenic temperature was something that was, let me say, subcritical from a technological standpoint. Okay. When people were using photomultiplier tubes for the detection of scintillation light in liquid argon, the time was very, very tough because the typical material that is used for the conversion of light into an electric signal in photomultiplier tubes is a photocathode, okay, which is a combination of alkali metals. And it's in the internal side of the detector. What happens is that this photocathode has a dependence of its resistivity on temperature that leads to a very strong increase in resistivity in a transition region which is between 87 and 200 Kelvin. So what it means is that you can take a traditional photocathode and use it very well at a temperature of 200 Kelvin for a xenon experiment, but for an argon experiment, it will totally misbehave. So at the beginning, sorry?
No, okay. Yeah, makes
At the
sense.
beginning of the year 2000, the solution that was found, and this is the solution on which the light detection is based still today on Icarus and in microburn, was to coat the internal part of the glass of the PMTs with a layer of platinum to provide strong conductivity. This platinum was killing a very significant portion of the light. It was a very significant trouble, okay? When we tried to develop with the same technology phototubes for dark matter, we had very mixed success. What is changing today completely the subject of detection of light, scintillation light in a liquid argon detector is the availability of silicon PMs. And in fact, the experiments that are looking at dark matter with argon are going fully with silicon PMs. But also the Dune experiment is going fully with silicon PMs. Phototubes you will no longer see in this kind of detectors. And with silicon PMs available, the detection of light becomes a much more effective tool so that you can project the ability through the detection of scintillation light of providing information which is indeed very useful for the determination of the agency, of the energy. And so a Dune-like detector, in a Dune-like detector, the light detection will not be an add-on, but will be a fundamental tool to lower the threshold of the experiment, thanks to this technological innovation and to the introduction of silicon PMs. Okay. Is this satisfactory?
Yes, a lot. I have also another question. Can I? About the background. So I imagine that for Dune, the energy range is of the order of the MeV. You are looking at that scale, right? So which is the background that was the environmental background that energy range? Now
in Dune, you look at events above 10 MeVs, I would say, okay? Because below 1 MeV, it will not even make sense. There is just way too much argon-39.
Okay.
Argon-39 is at the level of a kilobecquerel per ton, and it will be a huge rate of events below 1 MeV. 8 MeV is the threshold for neutron-induced activity. and a dune-like experiment will not have a control over radioactivity. So you will be full of neutrons that will cover the spectrum with instrument-driven background up to 8 MeV. So the minimum threshold for observation of solar neutrinos is at the level of 10 MeVs. You will find some information like this if you're interested in the lowest threshold for argon in the early papers with the proposal of using Icarus for making the measurements that eventually was made by Snow, charging the neutral currents. And there are some beautiful passages that were authored by John Bacall that are very illuminating in this respect.
Okay, so probably I don't understand then which kind of signal for the neutrinos. The neutrinos, you are looking at neutrinos through the pions, right?
Neutrinos, you start looking from 10 MeV up, okay? You look between 10 and 20 MeVs to the highest energy portion of the solar neutrino spectrum. For example, something that will be very interesting observing with the Dune experiment will be the HEP neutrinos. That is the only source perhaps that was never observed to date of neutrinos, which have a spectrum that extends up to 18 MeVs. Then above, you look between 20 and 40 MeVs to remnant neutrinos from remnant supernovas. And then in the range above, in the multi-GeV range, you look at the neutrinos which are generated by the neutrino beam at Fermi. Okay. Okay. So you look at the hadronic and you look at essentially the electromagnetic showers that are generated by the neutrinos. Okay. Okay, thank you.
Okay, we can move on with the question. Now it's time for Francesco Poppi.
Hi.
Hi, Francesco.
Good morning. I have one question and plus one which is related to the first one. The question is about the Dune near detector RTPC. My question is, does it have enough critical mass for the neutrino interaction observation? And I mean, the answer would be yes, because of course it's in the detector hole. But in general, how does RTPC behaves better than LRTPC? And yeah, and would LRTPC with the magnetic field around it be better than RTPC?
This is a very good question, and you should be in the review committee of that program because it's a question that has grappled the mind of many colleagues. We've been trying to unravel, why exactly you need 3 detectors in that suite of short baseline experiments. Can't you do the short baseline program with 2 or 1 detector and have the same level of sensitivity? I think it's a very smart question, and it's something, quite frankly, where I've seen a number of colleagues sitting in this committee, where I'm also part of, trying to grapple themselves with this question and never getting very straightforward answers on the matter. My personal impression is that the suite of 3 detectors could be possibly engineered in some way that you get the full complementary information on the neutrino field with a little less infrastructure. But this is a very delicate question that extends to many Monte Carlos covering the entire field of spectrum of these neutrino detectors, and it's very, very complex. I will say it's a little bit the detailed examination of that question, it's a little bit above the scope of this call, but it's a very, very smart question that has not found yet a definite solution. Okay.
Thank you. And as far as the magnetic field around the LRTPC?
Yeah, that is certainly
because that would be the main advantage of the RTPC, right?
Yes, yes, and that is of course a very important tool to separate events with different charges and to add some additional resolution on the understanding of the profile of the neutrino beam. Now, but to the level to which each one of the characteristics of the three separate detectors is really and truly fundamental to deliver the goal of controlling the systematics so that you can expand as much as possible the level of discovery of the CP violation to the level of the 5 sigma, I will say that's a question that has not been solved to the utmost satisfaction of anyone that has reviewed the system.
Okay. Thank you, Francesco, for your questions. Now there is a question on the chat that is, why is the liquid argon transparent to its own scintillation light?
Liquid argon is transparent to its own scintillation light because the scintillation light, it's a very complex question that has to do with the formation of dimers. Dimers are protomolecules, not stable molecules, are protomolecules that have a very short mean life. And it's the only form of molecular aggregation that is known among noble atoms. In other words, when you ionize a swath of gases of liquid argons, you introduce such a large perturbation on the atomic shells of the argon that you can create temporary bounds between two argon atoms. And these temporary bounds are responsible for a sort of molecular level attraction between two atoms that are released in a short time and that are responsible for the emission of photons in the ultraviolet range. But it's a characteristic of the quantum nature of this bound that the region where the emission is present is shifted with respect to the region of absorption of the atom itself in its steady state. And there is a beautiful study authored by former colleague of mine who's now at Queen's University, Alex Wright, that puts that into focus and shows why it is nearly impossible for this kind of dimers that are originated in noble liquids to produce light that is effectively absorbed by the neutral atoms. And it's a fundamental factor of nature that makes it possible to have a detection of scintillations in this system. And for example, makes possible the entire field of detection of dark matter with this kind of detectors.
Okay, thank you. There is another question. Robert, please.
Yeah, thank you. So there are, as it seems, many liquid argon TPCs currently built or already built at Fermilab, but there's also the NOVA detector, which uses calorimetric tracking. Is there any, is this a worthy competitor? Because I mean, they also have a very rich program in neutrino physics. Has there been any considerations to go with this technique, or is there, let's say, is this liquid argon TPC so much better in probably spatial resolution that there were not considerations to go with such a tracking calorimeter?
NOVA and T2K have the ability of advancing very significantly the understanding of neutrino oscillation. And I believe between the combination of the two of them, they will push also the sensitivity for CP violation in the leptonic sector well below the 3 sigma level. But the combination of the mass of the detectors, the distance of the oscillation, and the power of the beams is such that even under the best circumstances, with either Nova or T2K, you will not arrive at a 5 sigma demonstration of CP violation in the leptonic sector. And this is the main science motivation behind the development of the DUNE program and its competitor program for the 5 sigma discovery of CP violation, which is the program of Hyperchemicande.
So is this mainly due to the better spatial resolution, or well, better like?
It's not only that, because you can get at the 5 sigma even with a detector that is based on a Water-Cherenkov like Hyperchemicande, and even in the early days of the program of Fermilab, there was a choice between liquid argon and Water-Cherenkov, so you can eventually get with a Cherenkov system at the 5 sigma level. What really matters is the characteristic of the beam, which is the energy, the intensity, the distance of oscillation, the power, the number of events that you expect in order to arrive at these 5 sigma levels. The constraint on and the containment of the systematics.
Okay, but then, so in principle, this technique, so there's no, let's say, obvious flaw with this technique, rather with the location of the Nova detector or with the beam energy.
Sorry?
So this is not really based on the detector technique used by Nova, but rather by the location of the detector and the beam.
The improvement towards the ability to make a 5 sigma discovery experiment is really given by the new beam, the new oscillation distance, the characteristic of the beam. It could have been a Water-Cherenkov detector. Fermilab opted to go towards a liquid argon detector that will offer a much richer physics because it will have a very good resolution of the events.
All right, thank you very much.
Okay, I think we can stop now the answer. Let me, in the question time, let me remind you that this evening at 6:30 p.m. there will be a session devoted to discussion. So if you have any other question or something you want to discuss, we will postpone this at the session of the afternoon. So now, Christian, you can move on and go on with the second part.
Can we take a 2-minute break?
Okay.
So that I take a sip of coffee and I come back recharged. 2 minutes.
Okay, 2 minutes break for all.
2 minutes break for all, and I will be right back. Okay.
Okay. Okay.
Okay. I'm ready to go.
Okay, perfect.
Okay. Thank you for the break.
Please.
So dark matter with noble liquids. Let me start with the Xenon program, which is a program hosted in Gran Sasso, which has gone under many different type of iterations. Started with the Xenon 10, then migrated to the Xenon 100 program, Xenon 1 ton, Xenon N ton, which is the current experiment, and the future, which is Darwin. you will see that this is a type of detector that can operate both with xenon and argon, though with very, very different characteristics. But it's a so-called two-phase time projection chamber. Why two-phase time projection chamber? Because there is the main target, which is in liquid, and then there is a region on the top of the detector which is gaseous, and it's a very thin region in gas contained in the so-called ullage of the detector, which is the typical denomination in English for the little space of gas which is atop a bottle of wine. And this gas in the ullage of the detector is playing a fundamental and critical role. Why that? Now we're looking in the case of dark matter for very low energy signals, typically below 50 keVs. And we want to extract as much information as possible. So we come back to what we discussed at the very beginning of our lecture. We come back to the fact that we want to extract both scintillation light and charge. Scintillation light, we are very lucky because these targets, argon and xenon, they have a very, very, very bright scintillation light yield. Typical scintillation light yield in traditional scintillations, stilbene, pseudocumene, other organic scintillators, or in crystal scintillators, very special crystal scintillators. Typically, you emit of the order of 10,000 photons per million. When you go to noble liquids, okay, the first fact of nature, which is very important to keep in mind, that the order of magnitude of the scintillation is changing. You go from the 10,000 photons per MeV to of the order of 40,000 photons per MeV, which is a very significant change, very, very significant change. 40,000 photons per MeV. Not only that, but you can extract the electrons, so you can take electrons and you can drift them over a distance that is going from the bulk of your detector to until the point where they reach the separation surface between liquid and gas. So let's have a look, for example, at these schematics, which is idealizing a detector for a two-phase xenon time projection chamber. And after my shot of coffee, you see the location of the original event, which is marked S1, because in this region, you have the emission of the primary scintillation light. Scintillation light, which is diffusing around the detector, scattered by the Rayleigh scattering and bouncing off the walls, and is reaching the photosensors. In this case, for the xenon experiments, typical photosensors are photomultiplier tubes. And you have arrays of photomultiplier tubes both at the top and at the bottom of the chamber. Okay. So you have these photons that cover essentially the entire arrays of PMTs at the top and bottom of the chamber, but at the very same time, you have a vertical drift due to the presence of an electric field which is shifting the electrons from the original position of the event to the surface of separation between liquid and gas. And in the region where there is the surface of separation, there is the presence of a gate, a transparent gate right in front of the anode, which has the characteristic of increasing this field very significantly in this region, with two consequences. First of all, you enhance the probability of drifting the electrons from the liquid to the gas. So the electrons arrive at the surface, they see a very strong field, and they are shifted effectively into the gas in 2 or 3 attempts. Once the electrons are in the gas, they're accelerated by the electric drift field, and they produce a signal in a region where they are able to produce a signal which is essentially proportional to the number of photoelectrons without inducing a full avalanche. So in this type of detector, it's fundamental the fact that you have two types of signal: the S1 signal, which is the prompt scintillation light, and the S2 signal, which is a proportional scintillation from electrons that have survived the drift and the extraction into the gas. And you have two signals that are the so-called S1 and S2. A very important role in the field of dark matter detection is the discrimination of events that have a very strong ionizing power. These are events that can be generated by neutrons or dark matter, from events that have a minimum ionizing powers, events that are generated by beta or gamma backgrounds. And you see here the difference. Typically for an event due to a nuclear recoil strongly ionizing, you have a ratio of S1 to S2 which is small, or a ratio of S2 over S1 which is small. While for minimum ionizing events, you tend to have a very large ratio of S2 over S1. And the reason is well understood. If you have a strongly ionizing event, such as a nuclear recoil generated either by neutrons or dark matter, what happens is that the track is so thick and so dense that you have a process of recombination that leads to an effective destruction of the free charges produced by the ionization process. So much of the charge is essentially recoupled with electrons, and only a limited number of electrons and ions can effectively escape the very dense track. So in this case, the signal from the electrons that are drifting towards the anode and are extracted into the gas is very strongly suppressed with respect to similar energy events from minimum ionizing particles. Is this clear? Do you have any question on the scheme? Because this is a fundamental scheme that we will see coming up also in the argon dark matter experiments.
Can I have a question, please?
Yes.
Do you know about energy resolution of position of event in these liquid argon detectors?
Energy resolution of position.
Oh, I'm sorry. I'm not energy resolution, position resolution. So how clear we know the
energy or position resolution?
No, position. I'm so sorry.
Okay.
Position.
Position resolution is typically given. You can reconstruct the events by two methods. You can look at the distribution of the S1 signals, but this is a weak element in position resolution because the events are essentially uniformly dispersed across the bottom and top photosensor arrays. The strongest tool for position resolution is the S2 signal, because you have the difference between S2 and S1 gives you very precisely the depth in Z. Once you have the illumination signal coming from S2, you see even here at the top this colored distribution of the array of PMTs. You have a strong intensity right above the S2 generation point, and then the intensity is fading away. Okay. And so in this way, you have an intensity that is degrading very rapidly from the center to the side. And you have a very huge lever arm because the events are very, very close to the closest PMTs. And as soon as you move away from the closest PMTs, the signal is degrading rapidly. So typically, with this evaluation of the signal from the S2 signal, you are able to reach a position resolution which is a fraction of the size of the PMTs, typically the size of the diameter of the PNT divided by the square root of 10. Is this satisfactory?
Okay, thank you. But it's as I understand, the energy resolution of X and Y is in relationship of the PMT's diameters and the resolution of z-axis. I want to know.
You said again energy. Okay, that is
I'm sorry. I'm sorry. Position resolution. Yeah, I'm so sorry.
No problem. No problem. I get it now. Yeah, the position resolution is essentially a fraction of the diameter of the PNT. The rule of thumb is that it's the diameter of the PNT divided by square root of 10. Okay.
Okay.
The backgrounds, okay, the backgrounds are varied, and essentially the backgrounds is anything that can mimic a very low energy event that has the capability of bringing any resemblance to high energy, high density ionizing events. Okay, so let's have a look at the scheme from the xenon Anton detector. You can have a variety of signal that can induce these detectors. The most dangerous are intrinsic backgrounds, such as radon, krypton, and xenon 136. These are very dangerous because they can be removed only with great difficulties from a xenon load, and they end up representing the most significant backgrounds from the searches. Even if they don't produce highly ionizing events, high density ionizing event, now there are so many of them that the tails from the reconstruction can spill into the region of interest. Then you have neutrons, whether they are from alpha N or spontaneous fission from the construction materials, they can play a very significant role. Backgrounds from gammas, from any construction material that is containing gammas. Muons can also induce neutrons. Or you can have high energy neutrinos that can trigger eventually coherent scattering on the nuclides and can bring signals that are resembling the ones of neutrons. The experiments for dark matter are becoming so big, of the order of a few tons, and in the near future, a few tens of tons, that you cannot neglect the role of solar neutrinos. Solar neutrinos are essentially turning from a special and prized signal from the year of the solar neutrino experiments. They can turn very soon into a nasty background, because they will be so abundant that they will represent a primary source of background for the exploration of dark matter. Okay. And they come to form a background in two different kinds of ways. Now, first of all, because they scatter of electrons. And scatter very abundantly of electrons, and some of the scatters, just due to the conformance of the kinematics, are reconstructed, or better reconstructed. Some of the scatters result in very low energy electrons that produce a lot of signal into the region of interest. The second method is the so-called coherent neutrinos nucleus scattering, okay, where you can have neutrinos from the highest energy portion of the solar neutrino spectrum, or even neutrinos from the atmospheric neutrino spectrum, many tens of GeV, that result into the production of coherent scatters that is polluting the spectrum of these experiments at very low energy. And it is producing signals that are essentially nuclear recoils, which are on a one-by-one basis undistinguishable from nuclear recoils triggered by neutrons or by potentially dark matter particles. So there is a variety of background signals that need to be taken into account. The Xenon family of experiments has been the most successful one in pushing the boundaries for dark matter, boundaries of sensitivity for dark matter to the extreme values that have been achieved today. Xenon N-TON was a resounding success, and soon there will be in operation Xenon N-TON and its twin experiment at Fermilab, the LZ experiment. One ambition of the program with the Xenon-based experiment is to mount the so-called Darwin experiment, which has the ambition of reaching 30 tons of fiducial volume and 99.98% of rejection of background for a 30% nuclear recall acceptance, very high light yield, and be able to come very close to the fundamental limit to a fundamental limit in the search for dark matter particles, which is the so-called new line. The new line is the line of the signal that is coming from coherent scatter of neutrinos, which is corresponding more or less at the signal of 1,000 coherent scatter of neutrinos. Okay, this is the signal level beyond which it would be very difficult to go with the traditional dark matter detectors if you don't couple in the so-called directional signal. So these are some of the plots that could be gotten from the Xenon N-TON and Darwin experiment if you detect a number of genuine dark matter events, either alone in the xenon or with the complementarity of observation, either in argon or germanium. This experiment also has the ability of measuring very well low energy solar neutrinos, and in particular PP and beryllium-7 neutrinos that have been measured at Gran Sasso in real time by the Borex-Xeno experiment. Borex-Xeno experiment that has had the chance of bringing to rest the observation of the so-called transition around 1 MeV between two different modes of oscillation of solar neutrinos. You know that in the mechanism of oscillation of solar neutrinos that has been found in nature, we have two types of oscillation. Well above 1 MeV, you have oscillations in the vacuum, in the 8-minute trip that the neutrino takes from the sun's core to the Earth. But low energy neutrinos below 1 MeV, they oscillate primarily in the core of the sun, okay? And they oscillate in a condition where the oscillation is resonant in the sun core and driven by the presence of a very strong density of electrons. This strong density of electrons is essentially modifying the forward scattering probability of the neutrinos and inducing a very different pattern of oscillations that are resonant in the core of the sun, and that result in a marked difference of markedly different probability of preservation of electron neutrinos that are coming at low energy in the sun. Another target for the xenon-based experiment is the observation of supernova neutrinos, and they can also do the observation of neutrinoless double beta decay thanks to the presence in xenon in the xenon of an isotope xenon-136, which is a naturally emitting a nucleus that is a natural emitter of two neutrinos. And so it's a good candidate to study the possibility that in nature there is a neutrinoless double beta decay. The background budget of these experiments, when you go to the latest generation of experiments, is essentially dominated by two characteristics. Number one is the contamination of the experiment with radioactive noble gases. You have radioactive noble gases that are intrinsic to the detector, such as xenon-136 and xenon-137. And you have also some of them that are extrinsic, but are intrinsic to the material that are surrounding the detector, such as the radon-222, which is a very nasty beast to control. But you start having also very important contributions from events that are coming from boron-8. Boron-8 neutrinos through their scatter on the electrons of the detector. And these are the dominating backgrounds which are affecting and limiting the ability of this type of detectors to play a significant role in the search for the neutrinoless double beta decay. Here is a little scheme of the xenon detector, xenon 1 ton and xenon n ton, with a detector contained in a cryostat and shielded by a water tank. And this water tank is instrumented itself with a muon Vito, which is based on photomultiplier tubes. The time projection chamber, we go here into a very specific example, which is the one of the xenon and ton experiment. The time projection chamber holds a target of 5.9 tons of liquids. It is equipped with 494 PMTs, 3-inch PMTs, 253 in the bottom, 241 in the bottom, 253 in the top. It has a drift length of 1.48 meter and a diameter of 1.33 meters. Recycling of the light is very important. So there is a special material covering the sides, which is very highly reflective. And it's PTFE, also known as Teflon. Very highly reflecting, it's bouncing off a lot of the photons. And you see here some of the characteristics of the detector. You see starting from the top left, the electrodes, the copper elements that are defining the PMT arrays, the field shaping rings. You see some of the test fixtures for the cryogenic photomultiplier tubes, and some machining to produce the parts and the elements for the time projection chamber. One of the elements that are crucial in terms of their contribution to background in xenon and ton is the radon. Radon is one of the nasty beasts and probably one of the most important backgrounds across all the experiments in astroparticle physics. Comes from the TPC and the inner cryostat. It can emanate also from the simple pipe that is connecting the detector to the recirculation system. It can emanate from the pump, from the getter, from pipes and cables. Essentially, it's an omnipresent background whose existence is complicated by a very significant factor. Any type of low energy astroparticle physics experiment. And control of radon is one of the major thrusts and one of the major drivers of research towards improvement of astroparticle physics experiments. Okay, so at this moment in time, the field is busy with the commissioning and operation of the last generation of the xenon-based experiments, which are the xenon and ton NLZ, which we shall see next. And we expect that the first results from these two experiments may come out, I would say, in the span of a few months to 1 year. The sister experiment, or the brother experiment to xenon and ton is its American counterpart, which is the LZ detector. Very similar. Also in this case, there is a central cryostat with 7 tons of liquid xenon, surrounded by a Vito of a liquid scintillator loaded with gadolinium for the abatement of neutrons, all immersed in a water tank, which is serving as a Vito together for the scintillation light of the gadolinium, and also a muon Vito for any signal that is coming from the muons. You see here the TPC with its arrays, the top array of PMTs and the bottom array of PMTs. In this case, the dimensions are slightly higher than the dimension of the xenon detector, 1.5 meter diameter, 1.5 meter height. 7 tons active liquid xenon, but the fiducial is 5.6 tons, 50 kilovolts cathode, 494 PMTs, very similar to the case of xenon. Gas circulation at 500 liter per minute. You see here the assembled TPC, the insertion that happened in October 2019, just prior to the pandemic, into the cryostat vessel. And you see here some of the transportation, the special transportation of the cryostat and of the TPC in the underground experiment at SoUP in preparation for the deployment of the detector. LZ must be plotted for the very detailed accounting of its background. You see that this kind of experiment with the xenon-based experiment, when you account for all the backgrounds, those are not experiments that have exactly 0 background. You expect of the order of 10 events in the total volume after 50% nuclear recoil efficiency. The final estimate is the one of 5.66 events from electron recoils and 0.5 events from nuclear recoils. So a very important tool, this one of the xenon-based experiment, to advance our understanding of dark matter research. We expect that the xenon and TON NLZ will bring the sensitivity 1.5 order of magnitude beyond what is the best limit for dark matter today, and may as well result either into a discovery of dark matter or into the exclusion of a very significant portion of the space that remains open to exploration. The next topic is dark side, and it's the big topic of the next generation dark matter experiment in Gran Sasso, but I see that the time is coming up, 10:30, so I would like to stop here for today and leave room for questions. Is that okay, Mr. Chairman?
You have 20 minutes more. Yeah. You think you can stop?
Oh, it's until 10:45?
Yes.
Yeah, but I think I would like to stop here and devote some 10 minutes for questions, because the topic of dark side, I don't think I can cover in the remaining 20 minutes. It will take more time.
Okay, now we can open to questions.
I have a question.
Please go.
So how do we find out the fiducial volume from the, like, if we have a 50-ton detector, how do we find the fiducial volume from this?
Well, the fiducial volume is an important question, because let's have a look, for example, at this projection of the events offered by the LZ experiments, okay? You see that there is a region of events. There is a region of the detector where you have a very low background. And this is the region which is at the center in Z and at the center in radius. But as you move on the top and bottom, you see a lot of background coming from the photomultiplier tubes. And as you go to a very high radius, you see also a lot of background coming from the side of the detector. So any surface which is covered with the instruments is generating background. Gamma rays that are coming from the PMTs, from the Teflon, from the cryostat, and so forth. The primary tool for discrimination in the case of the xenon-based detector is, in fact, the so-called self-shielding. Self-shielding is a very important and fundamental tool for the rejection of background in xenon-based detectors. It's a very, very important tool because this tool is allowing you to reject events that are very, very close to the boundary of the detector. And so by Monte Carlo simulations, you must be able to calculate the boundaries of the region that are of interest for your detector, and you must be able to isolate the portion of the detectors that are where you have a high expectation of background event and being able to exclude them from your search for dark matter. Otherwise, you will be confused by an unbearable background. Is that a satisfactory answer?
Yes, thank you very much.
Any answer?
Other questions?
Don't be shy.
I don't think they're shy. Maybe they're just tired from the long lecture, because I see they had a lot of questions on the first part. Maybe
Yes.
the heat is making everyone tired.
So I have one argument that would like to listen to your idea. So one very important point in the dark matter experiment is to have a very low background, no? Have a very low threshold, sorry, very low energy threshold in the experiment. So can you remind to the audience which is the most important case to reach a very low energy threshold in this kind of experiment?
What do you mean by the case?
The point, the aspect of experimental aspect that allow you to have a very low threshold. So let me say what I have in mind. If as you shown, for example, in the case of xenon, the detector has been scaled since the beginning by a small one to a very huge one, no? And so naively, when you enlarge your volume, in some way you lose some light yield in your experiment, or and so this could affect in some way the number of photons that you are able to collect. So can this have an impact in the energy threshold? It seems not, because this experiment, when they scale up, they was also able to work with lower energy threshold. So it would be interesting to understand why in which way they was able to make this achievement, to enlarge the volume of the detector and to reduce the energy threshold.
So basically, the threshold in a xenon-based experiment is fixed by this experimental condition. A trigger that is useful for physics is a trigger of 3 different photomultiplier tubes in the span of 20 nanoseconds. Okay, so 3 photomultiplier tubes, 3 photoelectrons, is the physics condition that defines the trigger that is useful for dark matter. Okay, more or less. And the point that why these experiments have been able to scale significantly from 10 kilograms to 10 tons, which means scaling a factor 1000 in mass, which means in linear dimensions, if you scale a factor 1000 in mass, you scale a factor of 10 in linear dimensions, okay? The reason why they've been able to do so is precisely the reason that we have made clear at the very beginning of the talk. Namely, due to the quantum nature and properties of the dimers of argon and xenon, and the fact that they emit in a region which has, by nature of things, a very low self-absorption for the photons emitted in the neutral atoms, you can essentially go with very large dimensions with little prejudice for the light lost. Okay, you maintain, even by scaling the dimensions, a light yield which is fairly close to the ideal light yield that you have in a small-scale detector. And for this reason, you're able to grow significantly, in the case of the xenon experiment, by a factor of almost 1,000, with minimal loss in terms of energy threshold. In fact, the years have gone by in the span of the program, and the little experimental losses that may have been in the propagation side have also been recovered thanks to an improvement in time of the characteristics of the photomultiplier tubes.
Okay. Thank you. Thank you very much.
Yeah, if I may add on this point, so basically also about impurities that Christian of course mentioned, it appears that it is much easier to clean the water, for instance, that is the main responsible for the absorption of photons, rather than the electronegative impurities. So we managed to keep the xenon very much transparent. The best fit is 50 meters of absorption length, while the linear dimension of the detector are 1.5 meters. While it is not the same for the electronegative impurities, which affect the second signal, the S2 signal. Here you have to develop a very complicated purification system, as Guillaume explained yesterday, that is more tricky, definitely.
And thank you, Marco. And the reason why the purification becomes easier as you build larger detectors, at least in terms of activities per unit of volume, is because when you go to larger detector, the ratio of surface to volume decreases. Okay, you have a lower surface per unit mass, and the surface is the one that is problematic in terms of emanation of impurities and gaseous contaminants. Of course, when you go to larger volumes, the one thing that you cannot defeat is the total amount of contamination that is emanated into the system by, let's say, pumps and tubes and getters and so forth. And this is the reason why, for example, if you take an experiment like LZ, you see that the background is eventually dominated by the elements that are emanated from the detector, and the emanation happens in great part also outside the detector in the recirculation system, is emanated and then it's drawn into the detector in form of radon, okay? And this is very difficult to abate because the emanation is omnipresent. Even the last piece of pipe that delivers the argon to your detector will emanate some radon. And so this is very, very difficult background to tackle, essentially, and very, very difficult to, very, very challenging stuff to deal with.
Yeah, sure. But anyway, I think that Riccardo's point is the key point for the future. I mean, being able to lower this threshold would be a dream, at least for the next generation. So far, we cannot drop the requirement of having at least 3 PMTs, otherwise we are killed by accidental coincidences. This is true for PMTs. It's even more true with silicon PM, whose dark rate is higher, at least at xenon temperature. Then there are maybe some dreams. So if you can cover the lateral surface of the TPC with photosensors, this of course is a plus. Other ideas are to detect S2 directly in liquid xenon, another complicated stuff. In this way, you don't lose light in the interface between liquid and gas. But this is definitely the goal. Although we proved to be able to see the argon 37 line at 2.8 keV with xenon, but being able to reduce it by another step would be extremely relevant.
Even though I have to say, Marco, that covering the sides with PMTs could be a benefit for light yield, but could be a minus for the fiduciary volume.
Yeah, it's always an overall balance.
And what is very interesting to me, because, and I think let's bring it to the attention of the students, we have another 10 minutes to go, as I understand, is the role of silicon PMs, okay? So I've told you that in the argon-based neutrino detectors, silicon PMs are replacing steadily the PMTs. Okay? Experiments like Icarus and Microboon, the optical system was based on PMTs, 8-inch PMTs. You will see that in Dune, there will be only silicon PMs. Similarly, what you will see in the next lecture in DarkSide, okay, and there is this dual phase argon detector, which is based on a photo detection system where the PMTs have been completely eliminated due to a lot of frustration with the PMT supplier, Amamatsu, that was unable to produce PMTs that were working reliably at liquid argon temperature. We had to invest 6 years ago heavily in the direction of silicon PMs, and you will see the beautiful properties of these detectors. These are detectors that we build on our own. We build the entire photo detection system on our own and with materials that is much more pure than the PMTs. But the adoption in the xenon-based detectors has a problem. And the problem is exactly the one that Marco was hinting at before. The fact that there is a component of dark noise of these silicon PMs that depends upon the temperature of operation. It is very, very low at liquid argon temperature. Liquid argon temperature, the dark noise of this detector is much lower than the one of photomultiplier tubes. But at liquid xenon temperature, this dark noise is exploding. And if you have a dark noise that explodes, you come back hitting and damaging the element that Ricardo was mentioning before, which is the threshold, because the threshold is given by the combination of 3 different photosensing units that see a coincidence in more or less the span of 20 nanoseconds, okay, give or take. So you see that all these considerations are driving the technological pathway for the argon and xenon-based detectors in 2 different directions. That is my interpretation, but I would like to see the comments from Marco, who's a great expert in xenon-based detector.
No, but this was indeed the same. I have the same feeling. So the future direction for lowering the threshold for next generation is indeed on the table. There is a lot of R&D going on exactly for the various reasons that you mentioned. So far, we are going on with the workhorse of PMTs, but it's clear that it would be desirable to have a new photosensors for the next generation.
I think that in this sense, the project DarkSide, the project of DarkSide to build the photosensor by their own, it's something very interesting also for the future, because it is some way pioneering, because up to now no one experiment has built by the photosensor by their own, and so this can be something that can give new perspectives to this field, I think, because if the project succeeds, as all of us hope, it will be a breakthrough in the sense that you will be able to realize a photosensor tuned to your necessity, tuned to what you need for your experiment in terms of low background, in terms of the dark count. So I think this is something very interesting. I say for sure in the next lecture you will cover this topic, but now it is coming out, so we can. I would mention this point also for students. So there is a question in the chat by Volodymyr. He asked, "Do you know about PMT stability, PMT gain degradation?" So
PMT gain degradation, I know that in general, the PMT gain is not a problem if you operate above the region of transition between argon and xenon, because at 200 Kelvin and above, the gain of the PMTs is stable, because the photocathode is essentially working almost as if it were at room temperature. The gain of the PMT has always been a problem for the liquid argon temperature operation of low background photomultiplier tubes. And in fact, you will see later on the lectures of Dr. Alessandro Razzetto, which is the main developer of the photo detection unit based on silicon PMs. And all of these developments started back in time for PMTs, okay? Because he had to design a very special amplifier operating at 87 Kelvin to boost the signal of the PMTs. Because if the PMTs are operated at the nominal multiplication of 10 to the 6 in liquid argon, they degrade very rapidly. And they tend to have a lot of malfunctions, electrical discharges. So what we found out is that the changes in the structure of the PMTs that were needed to make them very low background, not only they did not address the issues of the sensitivity of the photocathode, but also led to a number of instabilities that forced us to operate the photomultiplier tubes at much lower voltage. And the difference in performance needed to be recovered thanks to a special cryogenic amplifier. The development of this cryogenic preamplifier is at the root of the development of the photosensors for dark side that you will see highlighted very significantly in the remainder of the school.
Okay, I think we are very in time. So if there are any, we have time for another question. Okay. Okay, I think that if there are no other questions, we can.
So Riccardo,
tell me.
From the organizer at this point, before the break, we would like to give a short announcement. I think you all will be very pleased. So if I can share my screen.
Please.
Thanks, Cristiano, and I think that also Cristiano will be happy to share this news with you all. Indeed, Elena Aprile is one of the members of the advisory board of this school, and yesterday we had the news that she received the Enrico Fermi Prize from the Italian Physical Society, and this is probably the most important prize in this institution, and this has been done for her pioneering efforts in the study of the universe, and in particular to improve the knowledge of the properties of liquid xenon. And so we are all very pleased for this achievement. Guillaume Plant, that you heard yesterday, is one of the senior person in her group, and so she made various efforts into this field, and so we would like to share the news with you.
Congratulations to Elena.
Congratulations to Elena.
Yes, it is very in time with this school, let me say. So
indeed,
very good.
And also good. Very well linked to the very well linked to the beautiful presentation that Cristiano just made.
Yes. Okay, I would like to thank again Professor Galbiati for his comprehensive and very good lecture, very interesting first lecture, let me say. So we can stop the session now, and we can reconvene in half an hour at 11:15 for the second lecture. So see you later.
Okay, in the meantime, Francesca put this flyer on the screen. And there is also the link to the place where you can already start having a look at the posters and the related videos. In the afternoon, we will have the poster session, but you can already go through it to prepare the ground.
Can I ask you a question about the posters?
Sure.
Yeah, I want to ask you, in Wonder, we have to simply, for example, I want to present a poster. I have to go in my area, then I have to wait that people interact with me, and then I can share the poster with them, right?
Exactly, exactly. So once they are in your circle, let's say you can talk with them, share the poster, share this, share a material and so on. And people then can add themselves to the conversation.
Okay, perfect. Thank you very much.
You're welcome.
Okay, hello everybody. It's time to start again the session. Now we'll move to Caroline Schaffner, that she's a researcher at Max Planck Institute and Gran Sasso Science Institute. She's the leader of the project called Cosinus that has been granted by INFN in 2016 and by Max Planck Institute. This project is devoted to the developing of scintillating cryogenic calorimeters made by sodium iodide crystals. So in this school, she will speak about the solid state detector. So also, as we made in the first lecture, I suggest you, Caroline, to divide your talk into parts. After more or less the first hour, you can stop and we can open the session to some questions, and then you can continue to conclude your presentation. Let me remind you that we have to finish at 1 p.m. So if you are ready, you can start.
Hello, can you hear me?
Yes, very well.
Okay, I try to share my screen then. Okay, let me see. You also see this red cursor? Is this working?
Yes, yes.
Oh, no.
Not yet in presentation mode.
Yeah. Okay. Okay. Presentation mode. Okay. Now? Okay.
Yes, it is working. Try to change the slide.
No.
No, we see just the first one.
Mm-hmm. It happens sometimes. It sounds.
Probably you have to keep the Keynote or PDF or Acrobat in the same screen, in the same desktop which you are connected with.
Yeah, so I have it, but okay.
This could be a possibility.
Okay. Okay, let's try again. Okay. So, is it fine maybe also like that? Yes. You can close this. Okay. Okay.
Okay.
Okay, then sorry for these technical issues. And yeah, hello everybody and welcome to this lecture on solid state detectors in underground searches. So when I actually got this invitation to do this talk, I was then when preparing the slides, I was reading this title more often, and in the end I thought it's good to look at it from reverse. So I will report you about underground physics. So this means actually we consider experiments which are in underground laboratories. And with that, I mean not like a couple of meters below ground, but labs with quite some rock overburden, and looking at experiments which are in this sector of rare event searches. So in particular—
Sorry, Caroline,
yes?
You can try to make Control L in order to have...
yes, I did before. I mean, it
does not work.
I don't know. No.
Okay.
Is it a problem like this, or?
No, I think we can, it's clear, we can see the slide anyway, so keep going.
Okay. I still cannot change it, is it? I have to do this. Very strange, okay. But is there something special to this Zoom? Because normally with me this works, so I'm quite astonished. Yeah, okay. whatever. Okay, so yes, I focus here on the dark matter and fundamental neutrino physics. And yeah, then it's on detectors, so it's not a theory lecture. You heard already a lot yesterday from Nicolao on dark matter interactions and Marco Pallavicini on neutrinos. So this lecture here will be mainly on detector physics, experiments, and then also results. And yeah, as it said, solid, of course, we will consider semiconductors, inorganic materials, and scintillators, and not gas or liquid targets like we have heard in the morning with Christian. Here's some short outline on maybe how these two lectures will be structured. So first of all, I would like to motivate a bit why we go underground. Then, yeah, as I said, direct detection of dark matter and neutrino-less double beta decay as these two big groups of experiment, which, from my opinion, fall in this section in the sector of the title's talk. Then, yeah, solid state detectors here. My main focus will be on this low temperature detectors, but I will also mention scintillation detectors, semiconductors, and also maybe this, if there's time, the skipper CCDs. I think about 2 to 4, you know from lectures, and I mean, this is something which is quite common, but maybe this low temperature detectors is something more special. And yes, I would like to devote more time on that. And then yes, there in the second lecture, I think on Thursday there, then I will report you on direct detection experiments, the results, also some maybe future of that, and the same for the neutrino-less double beta decay. Yeah, so why to go underground? So the motivation for doing this is that you, as you know, we are bombarded with primary cosmic rays coming from the universe. And this is actually a high flux of quite high energetic particles. And they typically create muons at around 10 to 15 kilometers from these charged pions. And then these muons, they just penetrate and reach whatever we have on Earth, of course. And this flux, if you are at sea level without any kind of coverage, and we have around 100 of these muons per meter squared in second. Here you see also a typical spectrum taken with an germanium detector of what we actually have at sea level. So you see here at the lower energies up to 3 MeV, we are mainly dominated by this ambient natural radioactivity from the uranium and thorium decay chains. Then there is this neutron-induced backgrounds and also the cosmic rays at the higher energies. If you now go to an underground site, you can reduce this flux of cosmic rays and products of it. And this is important if you would like to look for signals like dark matter or also neutrinos, which is rare events. You need to reduce these particles that you know, which we call the background, relative to the signal rate. So this minimization of this background, as I said, you can do going in an underground lab. And here I show the example of the Laboratorio Nazionale del Gran Sasso, which is a lab in middle of Italy. And there you, it's a lab which is very big. I will talk about more in the experimental section then about that. But there you have a rock overburden of around 1,400 meters. And this reduces actually the flux of muons that you have that can reach a detector by 6 orders of magnitude. So this is quite good because you end up then with around 1 muon per meter squared an hour, which is a lot better for then doing some rare event search. Then, of course, other backgrounds you have is neutrons, for example. So here I also quote the neutron flux below and above 1 keV, and the radon in the air is around 20 to 100 becquerel per cubic meter, which is similar to what you have above ground. And this is this is actually good because this lab in this case is ventilated, because otherwise you would have a lot higher radon background in such an underground lab, because you have this emanation of the radon coming from the rock itself. Okay, apart from going in an underground lab, there's other ways to minimize the background if you want to do a rare event search, and this is passive shielding layers, for example. So typically, the scientific collaborations, they cover the experiments with water or polyethylene, lead and copper, so you can use low Z material to moderate neutrons, for example, or high Z materials to shield gammas and higher energetic radiation. You can do this passive, just like really wrapping your experiment with a lot of layers of this materials, or you can do it active. For example, if you have a big water tank, you can equip this with photomultipliers and make it work as a Volta-Cherenkov veto. Same is true for plastic scintillators or liquid scintillators, of course. Another important issue, as we also heard before from the liquid noble gas experiments, is that it's radon, so you should mitigate radon. This is something one has to very much care of. And also then there comes, of course, the material selection when it comes to the detector itself. So this is to use only materials which have been screened before, so where you know that they have a low content of this natural decay products and other radioactive isotopes. And you also should handle them carefully, like typically in clean rooms, and you should avoid that you as a person also contaminate them just by touching and leaving them quite a lot of potassium 40 on them. Okay, furthermore, of course, this minimization of the background is fundamental if you want at some point to also do discovery. And furthermore, of course, your background. So if you have, if you want to have an experiment where the sensitivity goes with the exposure, the background best is 0. So yeah, the more background you have and the more background you don't understand, the less is the sensitivity of the experiment you can do. So this is very important and to be kept in mind. Okay, so now to this direct dark matter searches. Yeah, so we've heard from Nicolaou that there's a long list of possible dark matter candidates. I just want to repeat here some way of how we categorize them. So there is this like light dark matter particles, which is having a mass below around 1 GeV, and then there's some like more standard WIMPs, so this weakly interacting massive particles above a GeV. And reaching up to some 100 GeV. Then this direct detection, or better say the hunt for dark matter, is not only based on direct detection, but you can search in different ways. So typically there, we mentioned this 3. So there's this, what is called the indirect searches, where you would look for annihilation products in your detector. This typically is space-based experiments where you look for some X-rays or other products which could be produced when dark matter interacts with itself. Then there is this so-called collider searches, like for example at LHC, where you collide protons and then possibly produce also dark matter and look for this missing mass in your data. And yeah, so this is these 2 searches which I'm not talking about here in this lecture, but focus on this, what is called the direct detection, where you have a dark matter particle interacting with normal standard model particles and then producing a signal in your detector. You see already in this picture here that this direct detection is a wide field, so there's a lot of small and bigger experiments. In comparison to maybe this other 2 kind of searches where you have the need for big facilities like LHC or some space-based experiments. Yeah, so for this direct dark matter interactions, so the assumption is that you have particle like dark matter which then interacts with the standard model particle, and in the most common scenario what you get is a nuclear recoil. And yeah, if of course the dark matter becomes very light and goes to this low mass region, we can also see maybe the recoils on the electron, because the ones on nuclear recoils, the energy is not enough to produce them. So this is also interesting in something coming up in the last years. Okay, so if you then would like to understand what you see in your detector, you can calculate the rate. So therein goes the target mass and And for dark matter properties also, yeah, the density, the mass, and the velocity distribution, some cross-section. And yeah, so here you have then the differential rate where you have this integration then of the minimal velocity to produce such a nuclear recoil above the threshold to the galactic escape velocity. And yeah, you see here goes also in the nucleus. So you have a proportionality to A squared for this WIMP-like dark matter, and also the form factor of the nucleus of the target goes in. If you then plug in here numbers, so yeah, as I said, we have a dependence on the target, as you have just seen from this formula. So here, yeah, I did this for sodium iodide. So you see here what you would expect. So this is this differential rate here in the function of the energy, the recoil energy in this case. And you see that we have really extremely rare interaction rates that we expect. And the current limit from the liquid noble gas experiments xenon 1 ton is a limit of around 0.01 counts per kV ton in year. So this is really, really rare. And yeah, you see also that the recoil energies here, they're in the range of a few kV. So you also need to have very sensitive detectors. And unluckily, I mean, the spectra is also very boring. You have this very flat and featureless spectrum that you would expect here, assuming 3 different kinds of dark matter particle masses. Then you, of course, can say, okay, is this all we can do in this direct detection? Look for this nuclear recoils with this flat energy spectra, or is there something which is more a smoking gun signature in this experiments? And there is actually 2 distinct signatures which I would like to mention just briefly here. So there is what we call the modulation signature. And this comes because, I mean, here you see, so in galaxy, we have, this is immersed in some kind of dark matter halo, and then we sit here on the Earth, which moves around the sun. And yeah, this motion of the Earth causes then some relative modulation of the velocity, which then also results in an annual variation of the rate that you would expect. So and this goes, as I show here, just schematically, that you have some cosine behavior, which has the period of 1 year. It's a maximum in summer, in 2nd of June, and then goes down in winter and goes up. And yeah, it's in the low energy region of a few kV, as said before. And it's not known that there's a background which could mimic this kind of modulation signature in such kind of detectors. The other one, which I would like to mention here briefly, is directionality. So this is again the same. So we have this kind of wind, and the average direction of this wind through our solar system comes then mainly from this constellation of Cyngus. And this means actually if you have a detector where you can track the direction of a nuclear recoil signal. So imagine you have your WIMP, which then produces the nuclear recoil, and you can really track the direction. This is a way of discriminating then such kind of dark matter signals from common background events. And I show here just one example for such an experiment, which is called Mousse dark matter, where they use such nuclear emulsion films. So this is now liquid. So I, just as an example where they have some chance in seeing these tracks, but there's also other gas-based experiments which have the possibility to tell or give some information on this directionality of nuclear recoils. Then the other big part of this kind of detectors in these underground labs is neutrino physics. So just a quick reminder on the neutrino, which is maybe our best friend. So this is the most abundant matter particle in our universe. It plays important roles in cosmology. If you think about cosmic microwave background, for example, structure formation, Big Bang nucleosynthesis, but also astrophysics. If you just consider the energy which is taken away from a supernova, it's mainly carried by the neutrinos. And what we know from the neutrinos is that they have a small but not a zero mass, and they are very different in scale from the other fermions. And so also one question is if there's the CP violation in this lepton sector, maybe this could be also related to this observed meta-antimatter asymmetry which we have in our universe. So there's a lot of interesting physics and questions to the neutrino, and what we so far only know is, yes, the neutrino, they have a mass and they mix, this is certain, and also we have precision measurements on mixing angles and delta m squared. What we don't know so far is what is actually the nature of the neutrino, so is it its own antiparticle or not. About the also absolute neutrino mass scale, there's only limits. The recent one was, I think, now from the Katrin experiment on the tritium endpoint measurement. There's now a new limit of 0.8 electron volt, and also the neutrino mass hierarchy is not set, so if it is normal or inverted. And as I said before, CP violation in the neutrino sector. So there's a lot, open questions, and also with solid state underground detectors, we can work on these questions. One way is, the double beta decay, or better to say the neutrino-less double beta decay. First of all, I want to show you here now the two neutrino double beta decay. So here a neutron decays to a proton by the emission of 2 electrons and 2 anti-neutrinos. You all know that. It's a second order process allowed within the standard model. And it was first observed in 1987 by Elliott. And today this is measured by quite a long list of isotopes. Then this so-called neutrino-less double beta decay is a similar decay, just you don't have an emission of the 2 neutrinos as they are their own antiparticle here. And you have only, so the energy is taken away by these 2 electrons. And in the standard model, this is not allowed. So it's on lepton number violating process by unit 2. And it's forbidden. So if you would observe this kind of decay, this would imply immediately physics beyond the standard model. The expected rate for this neutrino-less double beta decay in comparison to this 2 neutrino beta decay is a lot less. And so far, there is no positive detection of this this decay. There was some hint for detection in the past by this Klaptor-Klein-Kothaus experiment, but this was disproven by the Gerda experiment already now some couple of years ago. So the isotopes of choice for this neutrino-less double beta decay, they are all only even nuclei. So I list here these possible isotopes of choice. And so here you can also see the Q value. If you remember the spectrum I've shown in the beginning, you've seen that this contribution from the natural decay chains, it goes mainly up to this thallium-diene 208 at around 2.6 MeV. So, and then it's quite, the background is less, let's say. So if you would like to do such an experiment, it's for sure clever to choose a high Q value, because there the background is less that you would expect. So you see here there's backgrounds which are above this thallium line and below. And then also another important factor is, of course, this abundance of this isotope then in the material, because if you have a really low abundance, like for the calcium here, you would have to enrich, which comes with cost. So this is quite some, you have to get some balance out of that advantages and disadvantages. The signature, as I said already, so is this, you get a peak at the sum energy of the 2 emitted electrons, and so you get somehow a monochromatic line at this Q value of the decay, and here you see this, this normal 2 neutrino beta decay. And so this is quite dominant to this small peak here. So if you build a detector, you have to make sure that you have a good energy resolution. Otherwise, this will be somehow covered or washed out in a way that you cannot observe this peak. Okay, just a quick summary on what I said so far. So we have dark matter and neutrino-less double beta decay. The energy scales are quite different. So for dark matter, we are more on this EV to KeV scale, whereas double beta is on MeV scale. The signal channel, is nuclear recoils. If we want to look for the standard WIMP-like or WIMP dark matter, and electron recoils once we go to really low mass dark matter particles. For the neutrino double beta decay, we look for this, the sum of the two electrons. For signatures, so in dark matter experiments, you can just look for this spectrum of the nuclear recoils, but also the modulation or the directionality, as I explained. And in the neutrino double beta decay, we have this characteristic peak at the Q value. And the target materials, there are quite a variety of materials that can be used in this kind of searches. I highlight here in red the ones which are solid. So for dark matter, we have the semiconductors with germanium and silicon, some alkali halides with cesium iodide, sodium iodide, then oxides, calcium tungstate, for example, or sapphire. And for the neutrino double beta decay experiments, there is searches with germanium, tellurium, selene, and lithium, and also some others. Okay, for both of these experiments, again, background is an important point. So there is external backgrounds, for example, neutrons, which can be muon-induced by alpha N or fission reactions. So this is mainly a problem with neutrons for the dark matter searches, and it helps to go underground because you can reduce this muon flux by 6 orders of magnitude. Here you see a sketch of different kind of underground labs in the world here. They have this muon flux versus the depth in kilometer water equivalent. And the deepest one is what is called the Xingping lab in China. Then there's Snow lab in Canada. Here, this LSMS is in France. LNGS is this Italian lab I mentioned in the beginning. And then there's some more shallow labs here. External gammas, they come from the natural radioactivity, the decay chains. So you have to make the material selection. Then internal backgrounds, we of course should avoid in liquid targets. We learned today morning that the krypton and radon emanation are the big enemies, and one has to be very careful in cleaning the liquid targets and also the surrounding materials from that kind of products which can emanate this isotopes. And then in solid targets, we have to take care also about activation and of course surface events, which can be alphas and betas decays. And for dark matter, there's also another issue, which is neutrino coherent nuclear scattering. So this is a background which once you're at a quite high sensitivity, which is a background you will see in your detectors. And this is very, very interesting and funny because it was observed only in 2017. And soon this big liquid noble gas detectors, they will reach sensitivity to also see this neutrino coherent nuclear scattering. And somehow these backgrounds of maybe today, they will also be the signal of tomorrow, as there's also a lot of science and to be learned from this neutrino nuclear scattering. Okay. So maybe then after this a bit overview on why underground and what physics we can do, I would like to give you some basics on different kind of solid state detectors that is used in that field. So just a very easy access to that is that we can think about, okay, what I actually can measure with such a detector. So there's what we call the phonon signal, which is normally almost 100% of the deposited energy, and it's very slow signals in the millisecond region. Then there is ionization in semiconductors that about 10% of the deposited energy can be measured, and this is quite fast signals. And then there is scintillation detectors where you measure the scintillation light produced by the interacting particle. Which is again also fast signals, but also only in the 1 to 10% range. Then, of course, you can think of building a detector which not only measures one of this kind of interaction, but you can make a dual channel detection, combining ionization with the phonons, or scintillation with the phonons, or scintillation with the ionization. yeah, so I will go through that different kind of ways of detection, starting with the phonons, and then going on with scintillation and ionization. So yeah, the phonons, as I said, so I'm a friend of low temperature detectors. They are, this abbreviation used for them is LTDs. And yeah, so a bit of history on this detector. So the first cryogenic calorimeter actually was working in 1935. This was 20 years or so later than actually the first time liquid helium was managed to be produced, which is somehow a prerequisite, because to arrive at cryogenic temperatures, which was used in the past, is of course the cooling with cold gases like liquid nitrogen at 77 Kelvin or liquid helium at 4 Kelvin. This was then followed up a couple of years later by Andrews by a first calorimeter using a superconducting transition sensor. And then there was also the first detection of a single alpha particle in such a detector in 1949. Today, this low temperature community, it is very big. So all started out with a new workshop, which was somehow held in 1987 at the Ringberg Castle. So it's called International Workshop in Low Temperature Detectors. The initiators, also initiators of this idea of using such kind of detectors for actually astroparticle physics, like looking for neutrino properties or dark matter. So this comes from this people here, which also are part, of course, of this conference. And this was held in the Ringberg Castle, which is a nice castle in a lake close in south of Munich. And from this time in the early or the late 80s, there was always a lot of follow-up of these conferences. It's on a biannual base, and the last one was in Milano 2019, and there is a next one now in July, end of July, but unfortunately remote at NIST. You see the community is big, and the reason for that is because this low temperature detectors, they are very flexible, so they can be used in a wide range of this energy scale here. So you can use them for mass spectrometry or heavy ion physics, so in the region of keV to MeV. You can detect alpha and beta particles with them, but you can also use them for astroparticle physics like dark matter or the stable beta decay, but also axions in this low energy region. So they really cover a wide range. And just to make this a bit more clear, even with the sizes. So here I show a very small, I'll explain later, a tungsten TS detector, which has only a mass of 3 picogram. And here on the other side, you see a huge germanium dark matter detector, which has about 1 kilogram. And they're both use like low temperatures for operation and this kind of thermal sensors for readout. So what is actually now a low temperature detector? So typically you have a crystal, you have this coupled to a heat bath, which brings it in the region of 10 millikelvin, and you have a sensitive thermometer, which allows you to read then the temperature change induced by a particle interaction. Just to make clear what it means, 10 millikelvin. Sorry. So here you see this Kelvin scale where we have like the temperature of the sun at 10 to the 7 Kelvin, and then going down you have here, for example, the melting point of tungsten, which is at 3,000 around 700 Kelvin. So tungsten is this wire which was used in this old-fashioned light bulbs. Then at some point here, 273 Kelvin is 0 Celsius, where water freezes. Then you have at 77 Kelvin, this is the temperature of liquid nitrogen. So if you liquefy air, this is more or less the temperature. Then helium, as I said before, 4 Kelvin, and then here at 0.01 millikelvin, this is actually the operation temperature of such low temperature detectors. And there will be a lecture, I will not talk about this, how you actually arrive at so low temperatures, because this is even colder than the universe. So yeah, there is special machines which is called cryostats, which allow to arrive at that temperatures. And there will be a lecture by Carlo Bucci on that, explaining to you how you can be so cool. So here again, some more details on what happens, or how such a signal formation happens in such a low temperature detector. So you have, for example, some X-ray, photon what interacting in your crystal. Then you get, so this photon creates a photoelectron, and then the photoelectron goes on creating electron hole pairs, and also again higher energetic phonons. And this electron hole pairs, they start to recombine again and produce phonons again, and this starts to down convert, and just more and more a down conversion happens and phonons are emitted. And if you just wait long enough, all this initial energy was deposited by the X-ray is converted in a thermal signal. And a detector which then can read this thermal signal, we call it a cryogenic bolometer or cryogenic calorimeter. Okay, so in some more details now again. So again, here this particle interaction, which leads to a temperature rise. There you have this crystal where you have to consider the heat capacity C. Then you have this thermometer, which typically is semiconductor or metal superconducting film. So you have also heat capacity, and then this is coupled weakly to this heat bath. And if you have now interaction in the KV region, this induces a temperature increase by some 1 to 10 microkelvin. And this temperature increase leads then, if you have a good thermometer, to this temperature pulse shown here. So you have a rise in some microkelvin, microsecond region, and then a decay in the millisecond region. And if you want to look on how this now depends, so you see here, so this, and somehow the amplitude of this temperature pulse is proportional to the deposited energy, considering also the heat capacities involved and also the decay time here. So this depends also on the involved heat capacities, and then the strength of the coupling of the thermometer to the heat bath. Okay, before I mentioned already that there's two different modes, so calorimetric mode and bolometric mode. If you have this calorimetric modes, the phonons, they flow in this thermometer more quick than they can flow out, because this is coupled very weak. And in the end, what you get with such kind of detector is an integration of this power input. And a bit the principle is like if you would measure filling levels, so maybe you all know this also from this physics exercise courses in the first semesters. And so again, here just the description of the pulse and the dependence, or this heat capacity. Then if you have a bolometric mode operation, there the situation is inverse. So there you have the phonons flowing in is lower than the flowing out. So they are quite strongly coupled thermometers, which allow for steady state measurement of the power input. And so in the end, you measure the flux. And here you have your signal given by the power input weight by the coupling of your sensor. Okay, so what about limitations of these detectors? Because of course this sounds all very nice. So where is the limitations? And so the limitations here come from what we call this thermodynamic fluctuation. So if you have with n this total, the number of excitations which have a mean energy of kBt, and you plug this in and calculate, you see you arrive at this formula here. There you see that the noise comes from this irreducible random thermodynamic fluctuations, which is due to maybe I go back here. It's due to the energy transfer in and out of these links. And in the end, this ultimate energy resolution that you can achieve depends on how well you can measure this temperature against these fluctuations. And there, of course, lower temperatures is better. So the lower you go, the better you are. And also, of course, reducing C allows to push this down. Then there is some also some intrinsic energy resolution to that. So you have here shown the thermodynamic fluctuation noise and the signal. And okay, there is something in between which is missing. So yeah, it's not only about this thermodynamic fluctuations, but there is also, of course, some noise coming from your readout, like the preamplifier. There's some Johnson noise because you have maybe an metal film thermometer or other discrete noise sources coming from also the operation, for example, of your cryostat. So because I mean, these experiments, they're quite complex. So there's a lot of, first the apparatus to provide the millikelvin, and then, you have to thermally couple everything well. So it's quite an advanced detection technique, which comes then, of course, with a series of other problems, but also, a lot of advantages, of course. Pro and cons. There's no requirement for charge transport, as for example in semiconductors, also no Fano limits. The absorbers for such kind of low temperature detectors, you in principle can choose from the catalog. So what you have to, of course, care about is the heat capacity. So metals are out, but all inorganic material, semiconductors, all kinds of crystals you can think of, they can be used. You can also decide for multi-targets. So as you heard in the morning, for example, this noble gas detectors, they are or xenon or argon, because of course you have this liquid. But with such kind of cryogenic detectors, you can also choose multi-composite targets, having, for example, this like sapphire, where you have aluminum and oxide atoms in. And you can do then detectors with small and large volume. The disadvantage is that signals, as I've shown you, are very slow, so they decay on a millisecond basis. This is, of course, horrible if you have a high rate, so because you would only have one pulse on top of the other, so you get huge pileup. This, of course, is not good. We now talk here about underground experiments, so your expected rate is already quite low, but still signals are slow, and you have to be careful about that. Then, the detector size, so there's the sensitivity scales inversely with the heat capacity. This you have to, of course, consider. You cannot do it as big as you want, and having still a good energy threshold, because this is correlated. And then, of course, you have to have a cryogenic facility which allows you to run at millikelvin, then you experiment. Okay, now we were talking a bit how in principle such a detector looks like. But now I want to give you more details on what kind of different thermometers you can use then to actually read out your signals. And just a reminder, so we talk here about thermometers which can measure energy depositions of a couple of or 10 or what kV, which lead to temperature increase in the order of some 10 microkelvin. Okay, so what kind of detectors we have? So there's what is called equilibrium detectors, where we measure thermal excitations. There's this what is called doped semiconductor thermistors, also NTDs. Then there is transition edge sensors, TS, and also metallic magnetic calorimeters. And then there's another group of thermometers, which is the non-equilibrium detectors, which is the superconducting tunnel junctions, for example, or also the M-kits. Due to limitation of time, simply we focus on these two sensors only, so the thermistors and the TS sensors, because this is also the ones which are used then in these experiments I will introduce to you and also show the results. But then in the next lecture, which is on Thursday. Okay, so some words on the semiconductor thermistors. So a thermistor, what it is. So you have some high impedance device, typically mega 2 gigaohm. And the resistance, it changes versus temperature. And you have some description of this change in temperature when going to lower temperatures. So you see this increases. And you can current bias it in a circuit like shown here with a JFET, and then read the voltage. There's two types. So one is a silicon thermistor, This you produce by ion implanting of phosphor and bore in a silicon material, and then you anneal it, and then you attach the absorber you want to read out. For example, this mercury telluride in this case shown here. And yeah, then you can get energy depositions in your absorber and measure it with your thermistor. The other group is based on germanium. It's called the germanium entities, so neutron transmutation doped thermistors. So this you do by exposing a germanium wafer to a high neutron flux at a beam facility. And then, of course, your material is hot, so you have to wait some time until things decay. Then you anneal it, and also you cut it in pieces. In comparison here to this very small thermistor for this high resolution X-ray spectroscopy, here you see a quite big piece of a germanium wafer. This is 3 by 3 millimeters. Here you see also this gold bond wires for then biasing it. And here is shown, for example, the resistivity versus the temperature. So you can see this can be characterized. And yeah, you can even produce different kinds of such entities depending on the dopant and also then the size and so on. So how does this work, this entities or the thermistors in general? So so how it was is called this variable range hopping. I don't know if you heard about this already, but what you have is like, okay, if you have a semiconductor, there's typically the band gap, which is below 2 electron volt for this germanium here. Then if you calculate the room temperature, this KB, you see this is in the, this is in the millikelvin region. So yeah, you need to dope if you want that there can be some free electrons. And yeah, at low temperatures, this situation is then different. So you can get then conduction via charge carriers, which hop in between this impurity sites. And this hopping works in a way. So if you now have a phonon, so you have a particle interaction that creates phonons, you at very low temperatures, then this electron here at this donor side can tunnel to the next side. And yeah, this is called then the hopping, and in that way you can collect your signal. Here's just shown in a different way. So again, this charge transport occurs around this Fermi level, so you can go from an occupied to an empty state. And yeah, this probability for this hopping is given here. Where you get this once you have an overlap of the wave functions, and as I've shown already before, you can even describe this the behavior of the resistance versus temperature shown also here, characteristic for your certain thermistor. So here R0 and T0 is value set by your thermistor, and then you can tune that. So this is actually very nice because you can do the sensor quite adapted to what you need. And I show here now an extreme example again of this mercury telluride absorber, which is very tiny. You see here, so this is really, really small. And then here an energy resolution at the 6 kV energy from this iron 55 line, which is 3.4 eV. So this is really a great result and shows how far you can go with this kind of the temperature detectors. This, of course, is now not for dark matter, not for neutrino detection. So this is a bit on the other side, showing how good you can do detecting like low energy X-rays or doing also X-ray astronomy, for example. Okay, the other next sensor I will introduce to you is the so-called transition edge sensor. So this is superconducting thin films, which are produced typically directly on an absorber. Here I show a picture from the CREST experiment of a tungsten film. This is this black film here, which is a superconductor having a transition temperature at 50 millikelvin. And here there's another 2 examples I show of B layer TS, because they consist of a superconductor and a normal conductor. this has a certain advantage in comparison to this, for example, tungsten TS, as by changing the thickness of these layers, you can somehow tune this transition temperature. And this is a bit higher, which of course depends if you don't need too much sensitivity, and higher transition is of course easier than for the cryogenic apparatus you have to provide. So in this sense, depending on your application, it can help that you can tune the transition temperature. Of course, if you want to do a very high sensitivity and low energy threshold experiment, it's of course good to push this as much down as possible. And you will learn in the lecture of Carlo Bucci that there is of course also some kind of technical limitation to the temperature, which is, I think the lowest one with the dilution refrigerators achieved without but an experiment is in the 2 to 3 millikelvin region. However, if you want to run an experiment, you are more in this 5 millikelvin region, a lot below. It's really difficult to go. Then, so how this works, so you have here, the transition temperature. So here you're normal conducting, then you lower the temperature, then at some point it becomes superconducting, the resistance drops to 0. And if you now imagine you stabilize your transition edge sensor in a way that you can sit here, if there's a particle interaction, you get an increase in temperature, which leads to an increase in the resistance, which you then can measure with proper readout electronics. Here again, I show this tungsten TS, and I just want to mention also that there's of course some noise contribution, which comes from the fact that the TS is a metal, it's a superconducting metal, but nonetheless you have Johnson noise, and also again Johnson noise plus the thermodynamic fluctuations I mentioned before, and this somehow sets the energy resolution you can achieve. And this is again ruled by TC, the transition temperature, and the heat capacity, the total heat capacity of your detector. Some other limitations to this kind of sensor come from the fact that this transition is, of course, not infinitely wide. So you have some linear range of it, and then it will be normal conducting again at some point. So if you have now an energy deposition, which is in the kV region, you have pulses which look like that. They are nice, they rise and decay, they are in the linear region. If you, but then, for example, have an alpha particle with a couple of MeV, this is completely driven out of the superconducting transition, and you get a pulse which somehow refeatures that fact that here you cannot change anymore the resistance, and then it goes down. So this is what we call saturated. You can with analysis reconstruct this pulse nonetheless and get quite some good also results on energy reconstruction and resolution. But of course, this means you have to, somehow tune your TS. So if you want to measure MEV scale, the TS has maybe better, a higher transition and a broader width. So this is something you can tune. So you can quite design this transition curve if you have a lot of knowledge in thin film production, which is, however, not obvious. Typically the experiments which run such kind of sensors, they have like for decades experience in producing thin films based on tungsten or other superconductors. So it's nothing which you would give to a company, for example, because it's not so easy. But once you spend a lot of time and brain in getting this going, you can also tune somehow these transitions and adapt them to the energy range you want to be sensitive to. About noise, okay, so here in red you see this measured spectrum, and in black the calculated sum. Here again it is in blue this thermal fluctuations. Then, as I said, we have this TS Johnson noise and some shunt noise from the readout circuit, and then there's this huge part of noise which is present in all TSs, but it's not really explained until today. Okay. How they are read out. So typically we use SQUID-based readout. So a SQUID is the abbreviation for superconducting.
We can, Caroline, sorry, we can stop a little bit to ask if there are some questions. I see that you have a lot of slides, but maybe we can stop for a while to see if all is clear up to now.
Sure.
A great number of information. So if there are any questions, you can answer.
Mm-hmm.
So I'll wait for the. No, it seems that okay. Yes, Giovanni Volta raise his hands, please, Giovanni.
Hi. I was wondering, you mentioned that you don't have any final factors for this coloring detector. Isn't it? I don't understand this. I mean, is what you show with the temperature fluctuation is not that the final factors at the end?
I mean, yeah, so I guess with final factor, typically this refers to semiconductors, right? Where we, where the creation, okay, so in a semiconductor, the creation of excitations is not independent for every carrier which is produced, because of course you have your nucleus and then the electron shells. So there is some kind of correlation, which in the end leads to lower energy resolution that you get than expected if you would have them statistically just independent. And this, of course, is good for the semiconductors, but something like that is not existing in that sense, apart from, as you said, of course, there is this thermal fluctuation noise, which but goes in the other direction, let's say, because it's a limitation really given by the fluctuations you have, and you can calculate going in and out of this thermal link that you have. Otherwise, you cannot cool your detector.
Okay, thank you.
You're welcome.
Okay, there is another question, another raised hand. Vatsa, would you like to speak or? Okay. He wrote. Okay, he wrote the question in the chat. So he's asking, is there a lower temperature working region for NTDs?
Is there a lower temperature region? So you mean, okay, so these entities, typically they also work in the region of 10 to 20 millikelvin, or also lower, depends a bit on how your NTD is, because in comparison to the TS, the NTD has mega and gigaohm. The TS is in the region of milliohm. So the readout is a completely different one. And of course, your electronics with which you read the signals, they should somehow fit also to the resistance range then of the operation of your NTD. And in this sense, the temperature matters. So the lower you get, the higher becomes the resistance, but you have to make sure that your electronics also is good with that, and also your shunts and so on. But other than that, you can quite tune that. Yes.
Okay, thanks. Other questions? Okay, if not, I think we can continue with, you can continue, please, Caroline, go on with your presentation. Thank you.
Yeah, sorry. Okay. So yes, I stopped here on saying, okay, how we read the signals with the transition edge sensor. So the NTDs, they can use normal JFETs, cold or in warm. And for this TS, it's a bit more complicated. So what we use is this, SoUP2021, the superconducting quantum interference devices, which is in the end nothing else than very sensitive sensors for magnetic field changes, which then are converted in a voltage signal. So here's, I just show a readout circuit. So you have your biasing current, which is here divided in the branch where you have your TS sensor. And here you have a coil, which is called the input coil to the SoUP20, and some shunt resistors and some reference. And now when here you have an interaction, then the distribution of the currents in these two branches changes. So you get then, so if it's here higher resistance, more current flows here. So you get a field change, which is seen by the SoUP20. And the SoUP20, I don't know if I should go in detail with this explanation on the SoUP20, but in the end, it transfers some magnetic field change in units of the flux quantum to a voltage signal. And you have a way of also somehow optimizing this by the bias current of your detector, because you should of course aim for a maximum signal. And yeah, maybe this is what I can say here, do not make it complicated. But in the end, okay, this is also commercially available, so you don't need to build it yourself. I mean, it consists of here the superconducting ring and 2 Josephson contacts. And yeah, so it's a commercially available electronics nowadays, and you can also use this for multiplexing, for example. Yeah, so the best, one of the best or lowest energy resolutions achieved with such TS sensors, I show here for some soft X-ray spectrum. Yeah, we have here again this iron line, and you see here now there's a full width of maximum resolution of 1.5 electron volts with a small gold absorber pixel. So this is really, it's really fantastic what you can do with this kind of and sensors. And yeah, it shows again this other extreme. So this is very small detectors, which is also called microcalorimeters. For dark matter and double beta decay, we are more on this macrocalorimeters region of gram and kilogram scale detectors, of course. For energy calibration, yeah, typically you have low energetic X-ray lines from sources, or you also can just shoot some heater pulses by a resistive heater you have on your crystal and use them then to get some energy calibration and also linearize your region of operation. Furthermore, these scripts, they can be used for multi-channels, so you can have a single pixel like shown here, but you can have also a multiplexed array. So you see here a lot of these pixels operated at the same time. This is something which, when I started or when I did my PhD, this was in the beginning that people started to use it, and now this is a standard technology, which is very nice to see. And here just some other examples for such an array operation. And some outlook. So this is again not underground and not solid, but it's such TS arrays which look for the cosmic microwave background at the South Pole. And here's again such sensors from the South Pole telescope and Atacama. Just that you know that it's not only used for dark matter or even metaphysics or double beta decay, but also for astrophysics. Okay, then I would now go on if there's no questions on the temperature detectors from the audience. No? I would maybe then go on with a short, very short review into the scintillation detectors. You all know from, I guess, lectures in universities, even school. So there's different kind of scintillators. So we have this inorganic materials, organic materials, plastic materials, and liquid noble scintillators, which we have heard today from Cristiano. And I will here just mention this inorganic scintillating crystals or also materials because they are interesting in this field because they allow for high precision, so you can get quite good energy resolution. There's crystalline oxides and this alkali halides, which are used in dark matter searches and neutrino-less double beta decay. And there is also dopants of this crystal then in order to have more activator sites, which allow them to have a higher light output. This is a very common technique and quite well understood, although the theory of the scintillation mechanism is nothing really understood until the end. I give you just a brief overview of that again. So we have band gaps there also, then you have a conduction band which is empty, and once you have again your particle interacting in your scintillator, you can move an electron from the valence band to this conduction band. And the same is of course for the hole, which then with the electron can create what is called an excitone. And this excitone can then transfer the energy it has to an impurity site. And yeah, this is somehow in this region of which is actually forbidden. And when it then relaxes down to ground state, you get this de-excitation, which comes with the emission of this scintillation light. Yeah, this is how this works for this inorganic scintillators. And yeah, so what about the choice of the material? So if you think about, yeah, I would like to do an experiment for dark matter. So how I choose my scintillator, if I want to go for a scintillator-based experiment. So of course, there's something which is you always have to consider is cost, and also the possibility that you can produce it. So the knowledge, someone has to have the knowledge to grow crystals, and you have to have the money to pay for them. Then, yeah, the density is an issue, because if you would like to look for, low energetic particles, low density is fine. If you would like to have, high ionizing gamma radiation, you need to think about that. A higher Z is maybe better. Then light yield might also be an issue, depends how sensitive you want to be. So again, if you want to do more lower energy threshold, a higher light yield is beneficial. Also pulse duration, again, depends what is the area you use it. For example, experiments which have a higher rate. Also, if I think about, like, I don't know, the lead tungstate crystals or cadmium tungstate crystals used in CMS, where you have a beam and you have a lot of particles interacting, and there's a high rate. Of course, a short scintillation light pulses is better than pulses which have a long duration. Then radiation hardness, again, in this aspect is important, because if you're at an accelerator, you have to think about that. For dark matter searches, this is more or less irrelevant, of course. Emission wavelengths also is important. So depending on what kind of photosensor then you use to register your photons, this is important. So for the standard PMTs, typically the green region is good, and infrared would be very bad. So you have to adapt this somehow. And a main point here, in particular for this underground searches, is of course radio purity. So this is a huge problem, because you want, of course, to have a detector which is not counting by itself so much that you cannot then look anymore for the double beta decay or the dark matter. So you have to make a selection of already the powder before you start the production of your crystal. Then you need to find a producer where they accept this kind of low radio, radio purity protocols of how you work on the machines, how you handle then the crystals, what you do with the furnaces, what kind of material you use for your furnaces, what production procedure you use, and if you then do some after treatment of the crystals, like zone refinement and so on. So there's a really long list you have to care about if you want to think about producing a radio pure crystal for your rare event experiment. So this is something very important, and it doesn't mean if it's commercially available that you also can get it radio pure. In the end, there's a lot of knowledge which goes into this really radio pure crystal production, and I will tell you later, but once we come to the experiments, I will show you how difficult it actually is and how many years it can take until experiments arrive at radio pure enough crystals for their searches. Here's just a table I copied from Saint-Gobain, showing some of this most used scintillators. So you all, I guess, know the sodium iodide, the thallium, which is a standard crystal and one of the oldest ones maybe which exists and is used. Then there's these LISO crystals for also laser applications, or the cadmium tungstate also used at accelerators for the detectors, or BGOs. So there's a long list, and there's a lot of different crystals available nowadays, and also you can get them from the single crystals with good quality, good light yield, and then depending on your application you choose, as I tried to summarize before. yeah, then something very basic. So yeah, the most common photosensor is still this photomultiplier, PMT. I guess you all have seen such a device already and for sure also used it. So typically, yeah, you have here your photomultiplier where your so the high energy particle comes, or also the low energetic particle comes, makes an interaction in the scintillator, then the photon gets in the photo multiplier, you get a primary electron, and then on the diodes you produce secondary electrons, and this goes on, and in the end you read your signal, which typically looks like that. So you see already the scale here is nanoseconds, it's not milliseconds, so there's 10 to the 6 in between, so this is really fast detectors, which is very nice, of course, and yeah, which is still the basis for most of the scintillator-based experiments. There will be a lecture from Alessandro Razzetto on PMTs, but also silicon photomultipliers and more on that in very much detail. So I will restrict myself to this here. Yeah, what is also
Caroline, there is a question in the chat. They ask about the why are light yield and light output not correlated? So maybe you're asking about light yield and light output in a scintillator. I mean,
the light yield and the light output. Is this here? Okay. So so there is an okay. So when you have this, sorry.
Yes, please go on.
No, okay. So yeah, so the light yield means so from so you have a certain number of photons that you get per kV. And I guess here the light output means then, so this is a conversion, because of course your photon has a certain energy, so you see then a certain amount of this deposited energy also in your photomultiplier. Is this what you mean?
Yes, that's right. Thanks.
Okay. So where we are, okay, there's of course this quantum efficiencies also going in that. I guess you all know that, and there's of course this different kind of phototubes. So if you choose your scintillator, then of course a suitable phototube is considerable to be used. So I don't know if you have the sodium iodide, which is here again in this 400 nanometer region emission. So this BI Kali, for example, is a good choice, or also others. But yeah, you have to take care about that this is matched together. So the emission wavelengths of the crystal to your phototube. Pros and cons. So yeah, so this is well established, working very well. You can get it commercially. So this scintillators and also phototubes is something really great. Absorbers you can choose from a long list, as I've shown you, and this was just some detectors of such scintillators. They can be small, they can be big. Signals is fast, so you don't have to worry so much about rate. And but in comparison to low temperature detectors or also semiconductor detectors, the energy resolution is worse. Okay. Then I would go on now with this ionization detectors, just also a very brief intro. So if you have a semiconductor and you apply a voltage, again, if you have an interaction with an external particle in this semiconductor, silicon or germanium, this photon can create photoelectrons. They go on creating again electron hole pairs, and they create also high energy phonons. This electron hole pairs, due to the applied field, they get separated, and the phonons they down convert again. So this is just going on, and in the end, yeah, all the energy is transferred to this electron hole pairs plus the phonons that you also get. Yeah, so this loss channels in this detection techniques can be some kind of recombinations, of course, if there's impurities, can be traps of holes, can be metastable states, and of course also the phonons. Yeah, just to say a bit now on what signals you get, very basic. So if you have silicon, you have this energy gap of 1.2 electron volt. Now, the number of created electron hole pairs is, but not simply just the division of this energy by the gap, but you have to consider rather this epsilon, which is the energy necessary to creating an electron hole pair, which is 3.7 eV for silicon and 2.9 for germanium. And for the noise, this goes a bit in this direction of the question we had before, that so this generation of this holes is not statistically independent, because of course you have this electron shells and there is some dependence, so it's not enough to take the statistical error, but you have this Fano factor, which in the end allows you to have a lower resolution than if you would just consider some independent, statistically independent just carrier production. Just to summarize this again, so this formation of this electron hole pairs requires both the conservation of energy and also momentum. So there is also additional energy which excites phonons, which of course escape this detection. This all is hidden then in this epsilon and the Fano factor. And for the thermal noise, for silicon, this is not such a big issue because the gap is bigger. However, for germanium, if you want to do good measurements, and it's impossible to do that at room temperature. So typically, this is why germanium detectors, you for sure also have always seen already, they are always immersed in liquid nitrogen for this reason, to reduce this thermal noise. In comparison now to the others, so they have really excellent energy resolution. You can also do big and small detectors. They can, they are fast also with the signals. Of course, you have to care about charge transport. It's limited to semiconductors, and in case you want to use germanium, you also need some cryogenics. In this case, at least some liquid nitrogen cooling. I wanted to show here again also. Some of this high purity germanium detectors already in basis for preparing then that we will have a look at the Gerde and Legend experiment for the neutrino stable beta decay, but also Edelweiss and CDMS for that matter. So here you have just a planar high purity germanium detector of a p-type. So on the here on this on and plus contact, you typically on this germanium, you evaporate a lithium layer. This is typically a couple of 100 micrometers thick. And then you have your PN junction region here formed. And this you do by inverse biasing this germanium. And then here you have the P plus layer, which is produced by implanting boron. And this is in some 100 nanometer region only. And this provides also the contact then for reading the charge signals. Then you can of course say, so this is the really basic germanium detector. You can also commercially buy and do then some screening or other gamma spectroscopy, interesting measurements. But of course, if you want to apply it for neutrino stable beta decay, you have to think about that, the maximum depletion that might not be enough in such a planar detector where you here have maybe 1 or 2 centimeters. So if you want to have just a bigger volume because you want to look for neutrino stable beta decay and you need to offer a lot of nuclei, you need a lot of germanium-76, it cannot go with a 10-gram detector. And in this case, a different detector shape is useful. And there was invented this so-called coaxial detectors that you have a thicker depletion depth, And yeah, here inside you have then this P+ electrode, and yeah, outside is N+. And the same is for this also new type of detector, which is called the BG detector, also used, for example, in the SCADA experiment. And yeah, this is just a different way of doing such a high purity germanium detector if you want to have a bigger volume. Here also some yeah, comparison now of a scintillator, here the sodium iodide to such a high purity germanium detector. So you see they're quite different in the possibility to in this achieved energy resolution. So this is quite nicely visible in this spectra. And yeah, here show, maybe I explain you a bit this SCADA detector. So here you have such an coaxial detector, and yeah, so this is the cathode again, and this is the anode. And then if you have now a particle trajectory, so like this green one or the blue one or the orange one, I mean, depending on, yeah, the holes have to drift here and the electron there. I mean, depending on the path they have to go through, you get the charge signal and the current signal, which, yeah, are very similar in shape, almost identical, but they are, yeah, shifted in time. And this kind of, yeah, the reader allows you actually to understand what event topology you have. So it allows you to understand what kind of particle was interacting. And this is particularly interesting because if you do this rare event search, it's a big bonus if you can say, this was a neutron, or this was a gamma, this was a alpha, this was a beta. I mean, it's very good if you can do particle discrimination, because it allows you to remove more of the background that you know and look better there where you want to search for new physics. And yeah, just here it's shown for some different, yeah, events. So here's some alpha particle, and beta, here would be a double beta decay, which is a single side event. So this is, sorry, I didn't write here. So this would be a single side event, like it would be the double beta. And you see this has a very characteristic yeah, shape for current and charge, in comparison to, for example, some multi-site event where you have, yeah, some scattering and deposition of energy in different parts of the detector, where you get this kind of signature here, this kind of signal here, sorry. And yeah, you can variate and do a discrimination, say, no, I'm not looking at multi-site events, I'm going to look at single-site events. And yeah, so this is quite nice. Okay, then I'm through with this yeah, brief introduction to the different yeah, detectors. And yeah, I could start now with the introduction of, yeah, the direct dark matter experiments, if there's not other questions to what I said before.
Don't be shy, ask questions. Okay, it seems that all is clear. So, okay, you can go on.
Okay, so yeah, so then I would tell you a bit about now the experiments. So here you just see a first map of the different underground labs we have where we can, yeah, put our experiments. So yeah, you see here's this in Italy, this LNGS, Moudon in France, the Snow Lab to mention in Canada, and here's in China this big, so it's now the world's deepest underground lab. LNGS was long time the world's biggest one in area. There's also one now at the southern hemisphere being built in Australia, and also in Argentina in this which is called Andes. And yeah, then there's a couple of smaller labs also spread around in Europe, but also US. Yeah, so just again, this overview on what kind of different experiments we have and what kind of signal detection channels they use. So this again, this plot I showed you before, just now filled out with this detector. So we have, if we measure only the scintillation light, we have here this inorganic scintillators experiments, but also single phase noble liquid experiments. If you measure only the ionization, there's the standard semiconductors for dark matter search, then there's noble gas detectors, and also the superheated liquids. Combining two signals, so having two signal channels, which typically comes with the benefit of particle discrimination. We have, as we heard already today from Cristiano, this two-phase noble liquid detectors with xenon, lux, dark side, and all the others. And then there is also experiments measuring ionization and phonons, which is called the semiconducting calorimeters, with germanium and silicon. And here the combination again with phonons and scintillation is the scintillating calorimeters with calcium tungsten and also sodium iodide. Out of those, you see not all is solid, or the minority is solid. And I will then go through all of them and tell you about the status and what is the results on them. So first of all, results in this direct detection sector, they are compared in this dark matter landscape plot, where you have this dark matter particle nucleon cross-section plotted versus the dark matter particle mass. And if you don't see any signal, you draw a limit and exclude a certain parameter space on top. And if you have a signal, you have this defined parameter space referring to a certain particle, dark matter particle mass at a given then cross-section. So this is what experiments do. You can, of course, question if this is useful, because you have to put in some assumptions, but this is how is this done in the direct detection community. Apart from a lot of limits and excluded parameter space on top, you have also this neutrino floor, where then neutrino nucleus coherent scattering would be a signal that you can detect in your dark matter detector. So the liquid or the gas detectors, they are very close already with their sensitivity to arrive at that level. And just to give you some idea on where you see what. So here is this region, this is the higher mass region where there's this classical rim. There's the sensitivity, the best sensitivity achieve experiments which have a large target, and also a large, where also like getting large exposure is of course easier. So if you have a ton detector, you can run a year and you have a huge exposure, which allows you to be very sensitive in this region. And obviously this is dominated by this liquid noble gas detectors, where scaling up in mass is more easy than if you think about some crystals, like to arrive at 1 ton. This is definitely more challenging. The sensitivity limit where these experiments are is around 1 event per ton in year. And here then you see this lower mass dark matter region, where sensitivity arrives at around 1 event per kilogram a day. So you see already this huge difference here. And in this region, there's a variety of different detector technologies which have sensitivity. This, I would say, is more this performance-driven sector, because you have to, of course, have a detector which has a low energy threshold in order to have sensitivity there. And so this is more widespread, where here really this liquid noble gas detectors completely dominate. Then there is some even far sub-GeV dark matter, which I will mention then on Thursday, which goes with this skipper CCD experiments, for example, for some very light dark matter searches. Okay. Okay, then going back to the slide here, I highlight now here in red all the experiments I will tell you more details about. And also here, you see again where they are. So a lot of them are in Italy, but also in SoUP in France, then here in Korea with Busan and Kim's, and yeah, SoUP, they have a site on both the northern and the southern hemisphere, and yeah, there's CDEX also here in China. Starting out with a lab which is in Italy, as the school is an Italian school. Yeah, there is this LNGS, which is in central of Italy. There's a motorway going through the Scansasso mountain, and there's a 10-kilometer tunnel. And once this was digged, they also built 3 big holes. And in this holes there is placed the experiments I will tell you about. The lab has also an external lab where there's a technical division, chemistry, electronic departments, space for researchers, workshops, and so on. There's also Mensa. And once you go underground, I mean, you can enter from the 2 sides of the mountain. So this would be now from this L'Aquila side, where you can drive in the tunnel. So there's 2 tunnels, one in one direction, the other one in the other one. And here is then just the entrance to the lab. So you would go in there, then the guards would let you in, and then you have this kind of underground tunnels which then guide you to the labs. It's very comfortable working in this kind of underground lab because you can go in with a shuttle and go out for lunch and go in again if you work there. So this is very different to, for example, the snow lab, underground lab, where this is part of a mine where when you go in, you remain in as long as you can, and then you just can go out once the miner's shift also finishes. So this is very different from the working experience. Also, once, as it's very big, once you're inside, you not even feel so much that you are so far below a mountain. And here is a closer sketch of the experiments which are located at Gansasso. So there's Daxite and Borexino, you heard about already from Cristiano. Then there's Sabre, I will tell you about because it's a scintillator experiment. Then there is Luna, which is doing nuclear physics. There's Cosinus being built at the moment. There's the Xenon-Bonton experiment. Then there's Dama here in between the 2 big holes. And then in hole A here, there's the Legend experiment and Gerda, which I will tell you about, but also Pest and Core in Kupit. So there's a lot of solid state experiments for dark matter and neutrino-less decay at Gansasso. And here I've just mentioned a couple of details on the lab to give you some impression that this is really also really a big underground facility. So again, to this comparison of results. So here you now have a quite updated plot of all the results from the different experiments I just mentioned. And again, here in this region, we are good with the cryogenic detectors because they have good performance, low energy threshold. But you see here also the liquid noble gas detectors are good. But in particular here, I mean, you see many orders of difference in sensitivity here down to the best limits of xenon, for example. And already, touching now. So this is the neutrino flow, however, for calcium tungsten, which is the target the CREST material, the CREST experiment uses. So all these experiments, as they plot limits, they see not a signal, so there is no of this dark matter WIMP-like observation yet. However, there is one exception. If you had a close look to that plot, so I show it again here. So you see these 2 islands which come from the Stava Libre experiment. And so this is an experiment doing a modulation search. And this is also the first category of experiments I would like to tell you a bit more about, starting out with Dama for today. So Dama Libra is an experiment at Gansasso. I've shown you they run a huge a target of 250 kilogram of sodium iodide crystals. I think each crystal is about 10 kilogram. They couple the crystals, you can see it here. They couple the crystals with phototubes. So here in this copper container is the sodium iodide crystal inside, and then they couple them here with the phototube. They read in the light signal, so they have no discrimination for beta gamma to nuclear recoils. The threshold achieved is 1 kV electron equivalent, and they are really traditional experiment because they run since more than 20 years. So this is really long. And they are the only ones, as I've shown you, that have an evidence for possible observation of dark matter in our galactic halo. So here is the result they have. So you see here the time distribution of this event rate plotted for, so this blue highlighted area here is what they call Dharma phase 1, which was 2003 to 2010. Then there was an interruption, and then there was what is called the Dharma phase 2 from 2011 to 2017. And you see, I mean, this, here the modulation, it's clearly visible, it's very significant, and you see also after the upgrade, it gets even more significant, and you see, they have a total exposure of 2.17 ton years of these two phases put together, and a very high significance of 12 sigma. So this is very clear, and they claim that this is a positive evidence for the presence of, as I said, dark matter in our galactic halo. And this is observed in a certain energy range of the data. So this is a plot from phase 1 where there was a threshold achieved of 2 kV, which was then with phase 2 lower to 1 kV. And this modulation signal they observed in the region from 2 to 6 kV. And this here is, for example, the spectrum for signal hits only. And you see that they have around 1 count per kV kilogram a day. So this is a quite low background. And you see here a small bump, which is due to potassium. And here you see then the plot combining the phase 1 and 2. So here was the last entry for the phase 1 with the threshold at 2 kV, and then it was lower to 1 kV. So you see a bit more how this behaves going 1 kV lower in energy threshold. And then there was, of course, a lot of cross check done from their side, but also from theory side, because you can imagine it's always interesting if someone has a signal, and especially if it's on the market for so long time, people try to find explanations for maybe a not dark matter origin. So there's a huge number of papers done on that. And you see here, for example, this is the modulation signal in the 1 to 6 kV region, and here it would be the region 20 to 10 kV. So you see there is nothing. And there's a lot of checks you can do also with single to multiple hits, for example. So again, you see here the modulation is present for the single hits, but while it's absent for multiple hits. And so of course, a lot of people tried to maybe find another way of explaining gamma, but they were not successful. And one has to say, the statistics of their signal is high, the period fits to this 1 year, as I said, which you would expect for dark matter, also the phase fits. And there is no convincing explanation on the market, although people tried really hard in the last 20 years. So this somehow puts a contradicting situation in this field, because you have this, this result and the others don't see it. And then you can, of course, ask if it's valid to compare, like it now, the Dharma results to xenon. So can xenon really exclude, for example, Dharma or not? Because also if you go back looking at this plot here, I mean, the island here, I mean, there's a huge number of orders, there's many orders of magnitude in between them. So it's really a huge discrepancy. And so the question is if you can really compare in the standard scenario or not. And we can have a look again at this differential recoil rate, where you plug in numbers, of course, if you want to plot your results in this framework. And there comes input from astrophysics, of course, on dark matter halo and velocity distribution, but also on particle physics. So in this interaction mechanism, and there goes in the form factor. And so you have some target dependence on that. And So that was developed the idea in the community that to really cross-check the Dharma Libra result, one has to do an experiment with the same target material. Yeah, so the target material is sodium iodide, so it consists of the light sodium and the heavy iodine. It's, as I already said, is a good scintillator and a multi-target, so you have these two compounds. They produce a lot of photoelectrons per keV. It's considered a good scintillator. If you dope the pure sodium iodide with thallium, you get also an emission wavelength which suits good the phototubes then. And yeah, from the production point of view, sodium iodide is easy. Can be done by, for example, Tucholsky method, but also others. And yeah, you can make also big blocks. So this is a known technology. The only really concern is the radio purity, because as already started to tell you a bit about. I mean, this is a crucial factor, and you need to find a producer which really takes care about that, because if the crystal is dirty, you will never arrive at a sensitivity to compare then or to Dharma, because they have very, very clean crystals for all what else is on the market. And yeah, then I mean, you can just not arrive at the same sensitivity. Then there's other nasty things on sodium iodide. For example, it's hygroscopic, so you have to always handle it in a controlled atmosphere. So in glove box, and flush it with nitrogen or some other gas, so you cannot just expose it to ambient air, because the humidity in the air would immediately attack the surface, and then you see what I show here. I mean, you get this kind of whitish spots, and if you leave the sodium iodide for some weeks on your table, it would just melt away like a solid crystal. Again, as I said, radio purity, and a really big problem in this material is this potassium 40. And this comes because it's very similar to sodium, so it is technically difficult to remove it. But it's also very dangerous for the experiment, because this potassium 40 undergoes this electron capture, and what you can get is this 3 keV Auger electrons, which are emitted together with the high energy gamma ray. And the 3 keV, if you go back a second, just ends up in this energy region of interest. I mean, 3 keV is here, and this is exactly, I mean, there where Dharma observes the interval, where Dharma observes the signal. So you would really like to make sure that the crystal you use has a very low potassium content. So there's a great number of now sodium iodide based experiments already running, or even being built or starting at the moment. So we have Anais in Canfranc lab, there's Sabre and Cosinus at Cansasso, then there is in this Yang lab Kim's, which uses cesium iodide, and Cosine, which uses sodium iodide. Then there's Picolone in Japan. And Sabre has, they have a site both in the northern and southern hemisphere. This is a nice feature of this experiment, because they want to make sure that this modulation is not based on some known background, so which would maybe reverse if you would go to the other hemisphere, whereas the dark matter should not. So this is a check in this direction. And there's also at the South Pole, there's the DMI's setup. What you should have to test Dharma is, of course, an energy threshold in the similar region of 1 keV electron equivalent now. If radio pure sodium iodide with a count rate of around 1 count per keV kilogram a day, which is what is achieved by Dharma. And as I emphasized before, this low potassium content. And in order to do a modulation search, so you cannot start out with a 1 gram detector or a 10 gram detector or 1 kilogram, but you should have some 10 kilogram of detector target if you want to do the check with a Dharma-like setup. Then you can, of course, say I add something in addition, for example, a liquid scintillator veto, because with this Auger.
Caroline, sorry if I interrupt you. We have 2 minutes
Yeah, I guess I can stop here then. You know, I anyhow have.
Oh, thank you. Oh, no, I don't know if you want to close this or I don't know.
Yeah, I just wanted, this is my last slide, so I just wanted to say.
Okay, no, so you have 2 minutes more to make a conclusion, so don't worry. Okay.
Yeah, so if you would like then to check DAMA and put something more, you could go for a liquid scintillator surrounding, because with this potassium, this 3 kV Auger electrons, there comes also this 1.4 MeV gamma. And if you could tag this with an outer scintillator veto, of course, you can also suppress then the 3 kV in your detector, or some muon veto on top of your setup, or a different detection technology which allows you intrinsically to discriminate nuclear recoils from electron and gammas, like for example, used in cryogenic scintillation calorimeters. But more on this and all these other experiments I tell you then in the next lecture, and I think I can stop here then.
Okay, thank you, Caroline, for this very good presentation. Now we have, I think that we can have just a few questions, because we are at the very end of the session. It's 1 o'clock. So Francesco Pop is asking in the chat if so I don't know if Francesco, you want to make the ask the question.
Yes, sure. Thank you. So my question is, So my question is, since the smoking gun of DAMA-like experiments is the seasonal modulation, the annual modulation of, say, the events, wouldn't it be more have more sense to have more experiments on the other hemisphere just to see the inverse modulation? I know that Sabre is one of those, but since the only experiment that saw it is in the northern hemisphere, I mean, maybe I'm just I'm not understanding. In my understanding, it would be better to invest more and more on the southern hemisphere instead of the northern one.
Yeah, so I mean, of course, I mean, on the map I've shown you that so far there were no underground labs on the other hemisphere. So this maybe is the first problem, because it's an infrastructure which you need to build, and it's not so easy because you have to dig, and digging comes with a lot of costs. So for sure now with this lab in Australia and also in Argentina, this becomes a very attractive possibility, and the Sabre experiment is doing it. So the idea is, I mean, the dark matter modulation, you would not expect that this changes, but what should change is, for example, if this, what DAMA sees, would be somehow related to neutrinos from the sun or some other seasonal effect that should change once you go to the other hemisphere. And definitely also, this is a very valid approach, and maybe also in the future it will become attractive for other sodium iodide-based experiments to just move their setup in another lab, because of course, one would like to understand what DAMA sees, and this is a possible check. Yeah. Also moving out of Gran Sasso, because it's, I mean, DAMA is in Gran Sasso, and for example, cosinus, for what I'm working, will be also in Gran Sasso, and Sabre is also in Gran Sasso. So if it would be related to some other background of this lab or so, I mean, of course, also changing the lab, not necessarily for maybe only to the other hemisphere, but anyhow, not being in the same lab could also help. I mean, it depends always on what you believe as an explanation, of course.
Okay, I see there is a raised hand. So Lucy, you can ask the questions, and this is, let me say, the last question. Then I recall that there will be a discussion at the end of the day, so we can postpone all the other questions for the discussion of the afternoon. So last question, please, Lucy, you can speak.
Hello?
So I see the raised hand, but I cannot hear any voice.
Maybe if you have problems with the microphone, you write in the chat or also on Slack or so.
She say, yeah, okay. He's writing that its microphone doesn't work. I don't know if you want to write the questions. Okay, say no problem. Okay, okay. I think okay. We will skip this question for the discussion of the afternoon. I thank again Caroline for the so you cover a very large number of topics. And okay, so I close the session here. Thanks again to the speaker and also to the audience for the question and to follow these lectures. Thank you.
Thank you. Bye.
Thank you.
Bye bye.